Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're setting our sights on something that, at first glance, shouldn't even exist. Imagine a star that has already died. Its fuel is gone. Its brilliant life has ended. The vast furnace that once fused atoms in its core has long since shut down. If the story ended there, it would make perfect sense. Stars are born, they shine, and eventually they die. That's the natural order of things, and yet scattered across our galaxy are objects that seem unwilling to accept that arrangement. They are the remnants of stars that exploded millions of years ago, dense, compact, and seemingly lifeless. By all reasonable expectations, they should be quiet. They should sit in the darkness, cooling slowly over cosmic timescales. Instead, every now and then they erupt. Without warning, they unleash bursts of energy so powerful that instruments orbiting Earth can detect them from tens of thousands of light years away. For a brief moment, a dead star screams. Then everything goes silent again. It's a little like discovering that a long-abandoned house occasionally turns on all its lights in the middle of the night. No one is supposed to be there. Nothing should be happening. Yet somehow, every so often, the darkness breaks. Those mysterious objects are known as soft gamma repeaters, often shortened to SGRs. The name sounds technical, perhaps even slightly intimidating. But behind those three letters lies one of the strangest stories in modern astronomy. Because these aren't ordinary stars, they aren't even ordinary dead stars. They belong to a category of objects so extreme that they push matter, magnetism, and physics itself to limits almost impossible to imagine. Before we begin untangling that mystery, though, I'd love to ask you something. Where in the world are you listening from tonight? Perhaps you're tucked into bed after a long day. Maybe you're curled up beneath a blanket while rain taps gently against a window. You might be listening from a bustling city where lights still glow outside, or from a quiet countryside where the night sky stretches overhead uninterrupted. And what time is it for you right now? Fitting questions, really. Somewhere above us, stars are living entire lifetimes. Others are being born, some are exploding, and a few extraordinarily strange ones are refusing to stay silent long after their deaths. Meanwhile, here we are, sharing a small moment together in our own corner of the universe. If you find this journey soothing, interesting, or simply a pleasant way to wind down before sleep, I'd be ever so grateful if you gave the video a like and perhaps subscribed as well. It helps this little corner of calm find fellow travellers who enjoy drifting off while contemplating things that are impossibly large, unimaginably distant, and occasionally very weird. Now, I should warn you, the universe has a habit of becoming stranger the closer we look. You might think you've developed a reasonable understanding of stars. After all, most of us learn the basic story fairly early in life. A star forms from a cloud of gas. Gravity pulls that gas together. The pressure becomes enormous. Nuclear fusion ignites. A star begins to shine. Eventually, after millions or billions of years, the fuel runs low and the star reaches the end of its life. Simple enough. At least that's how it appears from a comfortable distance. The trouble begins when astronomers start paying attention to the details. The universe, as it turns out, rarely settles for simple. Take our own sun. Every second it converts hundreds of millions of tons of hydrogen into helium. The process releases enormous amounts of energy, which eventually makes its way across 93 million miles of space to warm your face on a sunny afternoon. That's already quite remarkable when you stop to think about it. A gigantic sphere of plasma hangs in space, powered by nuclear reactions, and somehow provides enough energy to support nearly every ecosystem on Earth. Yet compared to some stars, our Sun is positively well behaved. Elsewhere in the galaxy are stars several times more massive. These giants live fast and die young. They burn through their fuel with astonishing intensity, shining brilliantly for a fraction of the time enjoyed by smaller stars. You could think of them as cosmic sports cars. Very impressive, very powerful, not particularly known for longevity. When such stars finally exhaust their fuel, gravity wins a battle it has been patiently fighting for millions of years. The star's core collapses. The outer layers explode outward. For a brief period, the explosion can outshine entire galaxies. This event is called a supernova. If you've ever seen artist impressions of supernova, they often appear elegant and colourful. The reality is considerably more violent. A massive star may spend millions of years carefully assembling heavier elements inside its core. Then, in a matter of seconds, much of that structure collapses. The resulting explosion launches material across space at millions of kilometers per hour. The blast waves race outward. Shock fronts form. Matter is scattered across interstellar space. Ironically, many of the atoms in your body owe their existence to these stellar catastrophes. The calcium in your bones, the iron in your blood, the oxygen you breathe. Much of it was forged inside stars that died long before Earth even existed. So whenever astronomers talk about exploding stars, they're not merely discussing distant objects, they're talking about events that helped make life possible. That's already a fascinating story, but tonight's story begins after the explosion, long after. Imagine standing in the aftermath of an enormous fireworks display. The brilliant flashes are gone. The noise has faded, smoke drifts through the air. The excitement seems finished. Most people would assume the show is over. Now imagine discovering that one of the fireworks shells occasionally explodes again years later. Not once, not twice, repeatedly. That would be surprising. Something similar happened when astronomers began studying certain regions of the sky during the 20th century. At first, the detections seemed almost accidental. A brief flash of gamma radiation would appear, then it would disappear. Days later, another flash might arrive, then another, then silence. The bursts didn't fit neatly into existing categories. They weren't behaving like known stellar explosions. They weren't acting like ordinary stars. And they certainly weren't behaving like objects that were supposed to be dead. The mystery deepened because these flashes originated from some of the most energetic forms of light in existence. Gamma rays sit at the extreme end of the electromagnetic spectrum. Visible light occupies only a tiny portion of that spectrum. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, gamma rays. Each step represents increasing energy. Gamma rays occupy the top end of that ladder. They're extraordinarily powerful. Fortunately, Earth's atmosphere shields us from most cosmic gamma radiation. If it didn't, life here would be considerably more complicated, and probably much shorter. The first astronomers who encountered these strange bursts couldn't simply point a telescope at them and see what was happening. Gamma rays don't behave that way. Detecting them requires specialized instruments, often placed above the atmosphere itself. As technology improved, scientists began gathering more data. Patterns emerged. The bursts were repeating. The sources remained in roughly the same locations. Something was generating enormous flashes of gamma radiation again and again. The objects responsible eventually became known as soft gamma repeaters. Even the name reflects scientific caution. Astronomers often name things before they fully understand them. In this case, they observed repeating bursts of relatively lower energy gamma radiation compared to some other gamma ray phenomena. Hence the name, simple, descriptive, and not particularly dramatic. Scientists have a long tradition of assigning very understated names to utterly extraordinary things. A black hole, for example, sounds like a minor plumbing issue. Soft gamma repeater sounds like a piece of office equipment. Neither description adequately prepares you for reality. As observations accumulated, the mystery only grew stranger. The bursts were astonishingly energetic, yet the objects producing them were incredibly small. Not small by everyday standards, of course, small by cosmic standards. Imagine compressing more mass than our Sun into a sphere roughly the size of a city. Not a country, not a continent, a city. The result would be something known as a neutron star. And neutron stars are among the most bizarre objects in existence. A teaspoon of neutron star material would weigh billions of tons. Their gravity is immense. Their structure is exotic. Their behaviour often seems more like science fiction than astronomy. Yet even among neutron stars, soft gamma repeaters stand apart. They represent an especially extreme subgroup, the overachievers of an already outrageous category. It's a little like discovering that among all Olympic athletes, a select few can also casually lift trucks. At some point, words like unusual begin losing effectiveness. What made these objects especially puzzling was their unpredictability. Astronomers could observe them for months without significant activity. Then suddenly, without warning, a burst would occur. The energy released in a fraction of a second could exceed what humanity produces in many years. Then the object would return to apparent calm. Imagine living beside a volcano that erupts without lava. No smoke, no warning tremors, just a brief flash brighter than anything around it. Then complete silence. That unpredictability became one of the defining characteristics of SGRs. They seemed calm until they weren't, stable until they exploded, quiet until they announced themselves across the galaxy. As researchers continued investigating, an even more astonishing possibility emerged. Perhaps these dead stars weren't powered by nuclear fusion anymore. Perhaps something else was driving the explosions, something capable of storing unimaginable amounts of energy. Something woven directly into the structure of the star itself. The answer would eventually lead scientists toward magnetic fields so powerful they challenge ordinary intuition. Fields capable of distorting atoms. Fields capable of affecting matter in ways rarely encountered elsewhere in the universe. Fields so extreme that they force physicists to rethink familiar assumptions. But before astronomers could understand why these stars kept exploding, they first had to understand what remained after a massive star dies. Because the journey from ordinary star to soft gamma repeater is neither simple nor straightforward. It involves supernovae, collapsing cores, neutron matter, and some of the strongest magnetic fields known to exist. The story begins with stellar death, but it certainly doesn't end there. Curiously enough, that realization forced astronomers to reconsider something many had taken for granted. Maybe a star's death isn't always the conclusion. Maybe, under certain extraordinary circumstances, it becomes the beginning of an entirely different kind of existence, one that unfolds in darkness, one that occasionally erupts with astonishing violence, and one that would eventually reveal some of the most extreme environments anywhere in the cosmos. A curious thing happens when we talk about stars. Most of us instinctively think of them as permanent, not immortal perhaps, but steady, reliable. The sort of objects that simply exist in the background of life. You look up on a clear night, and there they are. Generation after generation sees the same constellations, the same familiar patterns, the same points of light scattered across the darkness. It's easy to forget that stars have lifetimes. Very long lifetimes, certainly. Long enough that entire civilizations can rise and fall without noticing any obvious change. But lifetimes nonetheless. Every star that shines today was born at some point in the distant past. And every star shining now will eventually reach the end of its story. At least, that's what astronomers believed for a very long time. The life cycle of a star seemed reasonably straightforward. A giant cloud of gas begins to collapse under its own gravity. As material falls inward, the centre becomes hotter and denser. Eventually temperatures climb so high that hydrogen atoms begin fusing together. A star is born. From that moment onward, a balancing act begins. Gravity constantly tries to crush the star inward. Nuclear fusion pushes outward. The two forces reach a sort of agreement. Neither side wins, The result is a stable star capable of shining for millions or billions of years. Our own sun has been maintaining this balance for roughly 4.5 billion years. Quite an impressive record when you think about it. Most of us feel accomplished if we remember where we left our keys for more than a few days. The sun has successfully managed a gigantic nuclear reaction for billions of years without missing a shift. Yet nothing lasts forever. Eventually, every star begins running low on fuel. What happens next depends largely on how much mass the star possesses. Smaller stars tend to age relatively gracefully. Larger stars do not. Massive stars live dramatic lives and die dramatic deaths. They burn through their fuel at astonishing rates. The more massive a star becomes, the harder its core must work to resist gravity. That increased pressure drives fusion faster and faster. It's a little like spending money. If you have a huge fortune but spend recklessly, you may run out before someone with a smaller budget who spends carefully. Massive stars are the cosmic equivalent of enthusiastic spenders. They burn through their nuclear savings account with remarkable speed. As their hydrogen fuel diminishes, new fusion processes begin. Helium becomes carbon, carbon becomes heavier elements. Layer after layer develops inside the star. Astronomers sometimes compare the structure to an onion, not because stars make anyone cry, although some physics students might disagree, rather because different fusion processes occur in different shells surrounding the core. For millions of years this arrangement works. Then the star encounters a problem: iron. Iron is a remarkably useful metal for human civilization. For stars, however, it represents a dead end. Fusion reactions involving lighter elements release energy. Iron does not cooperate. Fusing iron consumes energy instead of producing it. Once a massive star builds a substantial iron core, gravity begins gaining the upper hand. The balancing act starts to fail, and when it fails quickly. The collapse itself unfolds with astonishing speed. For most of its life, a massive star changes gradually. Millions of years pass between major stages. Then, near the end, events accelerate dramatically. The core begins collapsing inward. Matter falls toward the center at tremendous speeds. Temperatures soar. Pressures become almost unimaginable. The entire structure loses stability. Within seconds, one of the most powerful explosions in the universe occurs: a supernova. Even today, the word carries a certain weight, and rightly so. A supernova briefly releases more energy than billions of ordinary stars combined. For a short period, a single exploding star can outshine an entire galaxy. Imagine lighting one candle, then another, then another. Eventually you have a room full of candles. Now imagine a single candle suddenly becoming brighter than all the others combined. That's roughly the scale of what happens during a supernova. The explosion launches stellar material outward at millions of kilometers per hour. Shock waves race through space. Heavy elements forged inside the star are scattered into the cosmos. Future planets may eventually form from that debris. Future life may emerge from those atoms. In a very real sense, supernovae help recycle the universe. They're destructive events. They're also creative ones. And for a long time, astronomers assumed the story mostly ended there. The star exploded. The star died. Case closed. Except the universe rarely closes cases that neatly. Even after a supernova, something often remains. The exact outcome depends on the original star's mass. Some stars leave behind white dwarfs, others create black holes, and some produce one of the strangest objects ever discovered: the neutron star. If you've never spent much time thinking about neutron stars, don't worry. Most people haven't. That's perfectly understandable. After all, they're not particularly common in everyday conversations. You rarely hear someone say, "Lovely weather today." By the way, have you considered the density of neutron degenerate matter? Yet neutron stars deserve attention because they represent one of nature's most astonishing achievements. When a massive star's core collapses, Gravity squeezes matter with extraordinary force. Electrons and protons are pushed together. The result is a vast sea of neutrons packed tightly into an incredibly small volume. The collapse eventually stops, not because gravity gives up. Gravity never really gives up. Instead, quantum physics intervenes. A bizarre pressure emerges from the rules governing subatomic particles. This pressure prevents further collapse. The result is an object containing more mass than our Sun compressed into a sphere perhaps 20 kilometers across. To appreciate how remarkable that is, it helps to scale things down. Imagine shrinking Mount Everest until it could fit inside a teaspoon, then increasing its weight until that teaspoon outweighed entire mountain ranges. That's not a perfect analogy, but it gets us closer to the sheer absurdity involved. Neutron stars are incredibly small by astronomical standards. They're incredibly massive by everyday standards, and they are incredibly dense by any standard at all. The surface gravity is equally extreme. If you somehow stood on a neutron star, which would be a very brief experience for multiple reasons, gravity would be overwhelming. A person weighing 70 kilograms on Earth would effectively weigh billions of kilograms there. Needless to say, packing for such a trip would be unnecessary. You wouldn't survive long enough to unpack. Yet despite these extraordinary properties, neutron stars initially seemed fairly straightforward. Astronomers discovered pulsars in the late 1960s. These rapidly rotating neutron stars emitted beams of radiation that swept across space like lighthouse beams. As they rotated, the beams periodically crossed Earth's line of sight. Tick, tick, tick. Regular, predictable, reliable. At first, the signals were so precise that some scientists jokingly wondered whether they might originate from extraterrestrial civilizations. The nickname Little Green Men briefly appeared during early discussions. Eventually, natural explanations prevailed, as they usually do. Still, pulsars were remarkable enough. Here were dead stellar remnants spinning hundreds of times per second. Some rotated with extraordinary precision. Others emitted powerful radiation. They seemed exotic, but understandable. Then soft gamma repeaters arrived, and suddenly neutron stars became much stranger. The first detections were confusing. Instruments recorded bursts of gamma radiation appearing from fixed regions of the sky. Unlike ordinary gamma-ray bursts, which typically occurred once and vanished forever, these sources repeated. The same location could erupt multiple times, days later, weeks later, years later. It was as though a supposedly dead object kept finding new ways to explode. This was deeply puzzling. Astronomers understood supernovae. A star explodes once. The event is catastrophic. The energy release is enormous. Afterward, the remnant cools and evolves. Repeated explosions weren't part of the expected script. Something unusual had to be happening. Imagine discovering a campfire that reignites itself every few weeks despite having no visible fuel. Eventually you would suspect that your understanding of the situation was incomplete. That is precisely what happened here. The observation suggested that neutron stars could remain active long after their parent stars died. Not merely active, violently active. And that raised an important question. Where was the energy coming from? Fusion was no longer occurring. The original star was gone. No obvious fuel source remained. Yet the burst continued. Scientists began searching for explanations. Rotation alone couldn't account for the observed behavior. Accretion from companion stars didn't fit every case. Something else seemed responsible. The answer would eventually emerge from one of the most powerful forces in nature: magnetism. Now, magnetism is something we encounter regularly. Magnets hold notes on refrigerators. Compasses point north. Electronic devices rely on magnetic fields. Most of the time, magnetism feels familiar, comfortably ordinary. Neutron stars do not do ordinary. A typical refrigerator magnet produces a magnetic field measured in a fraction of a Tesla. Earth's magnetic field is much weaker. Even powerful laboratory magnets generally remain within ranges humans can reasonably comprehend. Neutron stars, however, operate on entirely different scales. Some possess magnetic fields trillions of times stronger than Earth's, and among those, a special category exists: objects whose magnetic fields become so powerful that they challenge intuition itself. These objects are called magnetars. The name sounds dramatic. In this case, the reality earns it. A magnetar's magnetic field is so intense that it can distort atoms. It can influence matter at extraordinary distances. It contains enough stored energy to power repeated explosive events. Suddenly the mystery began making more sense. Perhaps soft gamma repeaters weren't simply neutron stars. Perhaps they were magnetars, dead stars carrying unimaginably strong magnetic fields. Stars whose magnetic energy continued building stress long after the original supernova ended. Stars capable of producing bursts that looked like explosions despite lacking traditional fuel sources. That idea transformed the problem. Instead of asking why dead stars continued exploding, astronomers began asking how magnetic fields could store and release such enormous amounts of energy. The shift was subtle, but important. The explosions were no longer viewed as leftovers from the original stellar death. They represented ongoing activity, a new process, a different source of power. The star's life had ended. Yet another story had begun, and in some ways that second story proved even stranger than the first, because magnetars don't merely sit quietly in space. Their magnetic fields twist. Stress accumulates. Energy builds. Eventually something gives way. When that happens, the consequences can be spectacular. The burst detected across thousands of light years suddenly become understandable. Not ordinary, not expected, but understandable. The dead star isn't truly coming back to life. It isn't restarting fusion. It isn't becoming young again. Instead, it is releasing stored magnetic energy accumulated within one of the most extreme environments in existence. And that realization revealed something fascinating. Death, at least in astronomy, is often less final than it sounds. Stars can die and leave behind objects capable of remaining active for millions of years. Objects capable of emitting radiation. Objects capable of spinning rapidly. Objects capable of generating magnetic fields beyond ordinary comprehension. And in the case of soft gamma repeaters, objects capable of erupting again and again long after their original stellar lives have ended. Let's shrink something familiar. Imagine taking a mountain, not a small hill, not a rocky outcrop beside a country road, an actual mountain, something enormous, something that dominates the horizon and makes human beings feel wonderfully tiny. Now compress it until it could fit inside a sugar cube. The weight remains, the mass remains, only the size changes. Already that sounds absurd. Yet what we're about to discuss makes that example seem almost modest. Because neutron stars are among the most extreme objects ever discovered, and without understanding them, soft gamma repeaters remain impossible to understand. The reason is simple. Every soft gamma repeater is believed to be a neutron star, not an ordinary star, not a black hole. Not some entirely separate category of object, just a neutron star pushed to extraordinary limits. And before we can understand why these dead stars keep exploding, we need to spend some time getting acquainted with the bizarre remnants left behind after some of the largest stars in the universe die. The first surprising thing about neutron stars is their size, or perhaps more accurately, their lack of size. When people hear the word star, they tend to imagine something enormous. That assumption is usually correct. Our Sun is roughly 1.4 million kilometers across. More than 1 million Earths could fit inside it. Many stars are even larger. Some giant stars are so immense that if one replaced the Sun at the center of our solar system, its outer layers would extend beyond the orbit of Mars. Stars are supposed to be huge. Neutron stars break that rule. A typical neutron star may contain more mass than the Sun, while measuring only about 20 kilometers across. That's roughly the size of a city. You could drive across one in less than an hour, assuming, of course, that driving on a neutron star were remotely possible, which it very definitely is not. Still, the comparison helps illustrate the scale, an object containing stellar mass compressed into something smaller than many metropolitan areas. Whenever astronomers first explain neutron stars to the public, there is often a brief pause. People assume they misheard. The numbers sound wrong. 20 kilometers. Surely not. Yet the measurements are real. The physics is real. Nature truly produces objects of this kind, and once you accept their size, another question immediately appears. How dense must such an object be? The answer is difficult to grasp, not because the mathematics is complicated, because the reality lies far outside ordinary human experience. Density is familiar enough. A feather is less dense than a rock. A rock is less dense than a piece of metal. We encounter different densities every day. Neutron stars operate on a completely different scale. If you somehow collected a teaspoon of neutron star material, it would weigh billions of tons. A single spoonful. Not a truckload, not a mountain, a teaspoon. Of course, obtaining such a sample would present certain practical difficulties. For one thing, neutron star matter only exists because immense gravity keeps it compressed. Remove it from that environment, and it would behave very differently. Also, getting close enough to collect a sample would likely be unhealthy. Astronomy occasionally has that problem. The most interesting objects tend to be the least accessible. Still, the comparison remains useful. A teaspoon containing billions of tons helps convey the extraordinary density involved. Every atom, every particle, packed together under pressures almost impossible to imagine. And yet density is only the beginning. Gravity provides the next surprise. On Earth, gravity feels ordinary because we've experienced it our entire lives. Objects fall downward. We remain attached to the ground. Everything behaves as expected. Neutron stars take that familiar force and increase it dramatically. The surface gravity of a neutron star can be hundreds of billions of times stronger than Earth's. That number is so large it almost loses meaning. Human brains aren't especially good at visualizing hundreds of billions of anything, but we can approach it indirectly. Imagine jumping. On Earth, you rise briefly before gravity pulls you back down. The entire process feels effortless. Now imagine attempting the same thing on a neutron star. You wouldn't rise at all. The gravitational pull would be overwhelming. Even standing upright would be impossible. Fortunately, this remains a purely hypothetical problem. No one plans to vacation on a neutron star anytime soon. At least not this century. Perhaps not any century. The escape velocity tells a similar story. Earth's escape velocity is about 11 kilometers per second. Rockets must reach that speed to leave the planet permanently. For neutron stars, escape velocities become a substantial fraction of the speed of light. Light itself struggles to escape their gravitational influence, not enough to become a black hole, but enough to create some fascinating effects. If you stood near a neutron star and somehow survived, time itself would pass slightly differently compared to someone far away. Einstein's theory of relativity predicts this. Strong gravity alters the flow of time. The effect exists around Earth too, it's just much smaller. Near a neutron star, the distortion becomes significant. Yet even these astonishing properties don't fully explain why neutron stars fascinated astronomers so quickly. Part of the excitement came from their rotation. When a massive star collapses, conservation of angular momentum comes into play. This principle appears throughout physics. A figure skater pulling in their arms spins faster. A spinning office chair rotates more quickly when someone tucks their legs inward. The same principle applies on vastly larger scales. A giant star collapses. Its size decreases dramatically. Its rotation speeds up. The result can be astonishing. Some neutron stars rotate several times every second. Others spin dozens of times per second. A few rotate hundreds of times per second. Imagine something heavier than the sun rotating hundreds of times each second. It's difficult to picture, yet such objects exist. They are among the fastest spinning things in the universe. This rapid rotation helped astronomers discover pulsars. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, those beams sweep through space. If Earth happens to lie in the path of the beam, astronomers detect regular pulses. Tick, 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 like a cosmic lighthouse. The timing can be extraordinarily precise. Some pulsars rival atomic clocks in their consistency. For years, pulsars represented one of the strangest categories of objects known to science. Then astronomers found neutron stars that were stranger still. Not all neutron stars behave like reliable lighthouses. Some seem restless, unstable, capable of sudden outbursts, capable of releasing astonishing amounts of energy without warning. Those objects eventually led scientists toward the phenomenon we now call soft gamma repeaters. But before that mystery could be solved, another mystery needed attention: magnetism. Magnetic fields surround us constantly. Earth possesses one, the sun possesses one, your refrigerator magnet possesses one. For the most part, magnetic fields seem rather manageable, useful even. Neutron stars once again ignored normal expectations. The magnetic fields associated with some neutron stars proved so intense that researchers struggled to find suitable comparisons. Earth's magnetic field is relatively gentle. It protects us from charged particles arriving from space. Compasses respond to it. Birds may use it for navigation. Useful, important, comfortably familiar. A neutron star's magnetic field can be trillions of times stronger. Trillions. Even that number fails to capture the reality. Imagine placing a refrigerator magnet beside a neutron star. The comparison would be almost meaningless. The difference is simply too large. It's a bit like comparing a candle to a supernova. Technically, both involve light. Practically speaking, they occupy entirely different worlds. Scientists eventually realized that some neutron stars possess magnetic fields far stronger than even ordinary neutron stars. These extreme objects became known as magnetars, and magnetars changed everything. Because once astronomers started examining their behavior, a pattern emerged. The mysterious repeating bursts of gamma radiation appeared connected to these magnetic monsters. The connection was revolutionary. Previously, stellar explosions were associated with fusion. Fuel burned, energy emerged. The process made sense. Magnetars suggested an entirely different mechanism. Perhaps magnetic fields themselves could store extraordinary amounts of energy. Perhaps dead stars didn't need nuclear reactions to produce dramatic events. Perhaps magnetism alone could power the bursts. The idea sounded unusual, yet observations increasingly supported it. To appreciate just how extreme magnetars are, consider what their magnetic fields can theoretically do. At sufficiently close distances, the field could interfere with electronic equipment. It could affect atomic structures. It could influence matter itself in remarkable ways. Fortunately, all known magnetars remain comfortably distant. Astronomers generally prefer studying them from afar. This is one of the advantages of astronomy. The most dangerous objects are usually very far away. The universe provides many fascinating things to observe. It also provides generous safety buffers, most of the time. What makes magnetars particularly important for our story is that they reveal an unexpected truth about stellar remnants. Death does not necessarily mean inactivity. A star may stop producing energy through fusion. Its bright stellar life may end. Its outer layers may be blasted away by a supernova. Yet the remaining core can still possess extraordinary energy reserves. In magnetars, those reserves are stored within the magnetic field itself. The field twists, it evolves, stress accumulates. The object remains active long after the original star disappears. That realization forced astronomers to rethink what stellar death actually means. For centuries, people imagined death as a final state, something quiet, something static, something complete. Neutron stars challenge that idea, especially magnetars. These remnants are not quiet corpses drifting through space. They are dynamic objects, changing objects, occasionally explosive objects. The original star is gone. Something stranger remains. In many ways, neutron stars occupy a fascinating middle ground between ordinary stars and black holes. They are born from catastrophic collapse. They possess immense gravity. They contain exotic matter, yet they remain visible, observable, accessible to scientific investigation. Black holes conceal much of their internal structure behind event horizons. Neutron stars leave their mysteries partially exposed. Astronomers can study their surfaces, measure their magnetic fields, track their rotations, observe their eruptions, and each new observation reveals another layer of complexity. The deeper researchers looked, the stranger these objects became. Their densities challenged intuition. Their gravity stretched imagination. Their rotations defied expectation. Their magnetic fields approached absurdity. And among them existed a small group displaying behavior even more unusual than the rest. Objects that periodically erupted with bursts of gamma radiation. Objects that seemed determined to remind the galaxy they were still there. Objects we now recognize as soft gamma repeaters. By this point, the picture was beginning to take shape. A massive star dies, a supernova occurs, a neutron star remains. In rare cases, the neutron star possesses an extraordinarily powerful magnetic field. That field stores enormous amounts of energy. Eventually, something triggers a release. A burst appears, then another, then another. Yet many questions remained unanswered. Scientists now suspected they were dealing with magnetars. But suspicion is not proof. Astronomy requires evidence, observations, patterns, connections that can withstand scrutiny. Long before astronomers understood what soft gamma repeaters actually were, they first had to confront a far simpler question. What exactly were they seeing? That might sound obvious. After all, modern astronomy often feels wonderfully organized. We have categories, classifications, databases, and decades of accumulated knowledge. When a new object appears, scientists can usually compare it against thousands of previously studied examples. But every now and then, the universe presents something that doesn't fit neatly into any existing box. And when that happens, confusion arrives before understanding. The story of soft gamma repeaters began during a period when astronomy was expanding beyond the limits of visible light. For most of human history, the sky was observed with eyes. Then telescopes arrived. Later came photography. Eventually, scientists learned to detect forms of light completely invisible to humans. Radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays. Each new window revealed a different universe. Objects that appeared calm in visible light sometimes proved remarkably active in other wavelengths. The cosmos, it turned out, was far busier than anyone had imagined. Gamma rays were especially intriguing. These are the highest energy forms of light known. They emerge from some of the most violent events in existence: supernovae, black holes, colliding neutron stars, nuclear reactions. Extreme environments tend to produce gamma rays. That made them valuable tools for astronomers. Unfortunately, studying gamma rays presented a challenge. Earth's atmosphere blocks most gamma radiation. This is actually very good news. Without that protection, life on our planet would face considerably greater difficulties. The downside is that astronomers cannot simply place a gamma-ray telescope on a mountaintop and start observing. The instruments must operate above the atmosphere. That requirement became achievable during the space age. As satellites began carrying scientific instruments into orbit, researchers gained access to entirely new views of the universe. Interestingly enough, some of the earliest gamma-ray discoveries came from spacecraft that weren't even designed primarily for astronomy. During the Cold War, several satellites were launched to monitor compliance with nuclear test ban treaties. Their mission was straightforward: detect gamma rays produced by nuclear explosions. If a country secretly tested a nuclear weapon in space or in the atmosphere, the satellites would notice. Simple, at least in theory. Then something unexpected happened. The detectors started finding bursts of gamma radiation coming not from Earth, but from deep space. This was rather surprising. The satellites were searching for evidence of human activity. Instead, they discovered mysterious explosions occurring across the cosmos. Astronomy has a long history of benefiting from unexpected observations. This became one of the most famous examples. Scientists soon realized that gamma-ray bursts represented an entirely new phenomenon. The challenge was determining what caused them. At first, nobody knew. The bursts appeared suddenly. They lasted from fractions of a second to several minutes. Then they vanished. Some seemed incredibly distant. Others remained difficult to pinpoint. The available data was limited. And limited data often leads to creative theories. Astronomers proposed numerous explanations: colliding stars, exploding stars, black holes, exotic particles, alien civilizations. Well, perhaps not many serious scientists favoured the alien explanation, but it occasionally appeared in public discussions. Whenever something mysterious happens in space, extraterrestrials inevitably receive at least honorary consideration. As observations improved, gamma-ray bursts gradually became better understood. Many turned out to originate from catastrophic cosmic events, occurring billions of light-years away. Huge explosions, one-time occurrences, powerful but brief, case mostly solved, or so it seemed. Then a handful of sources began behaving differently. Very differently. Most gamma-ray bursts appeared once and never repeated. Astronomers could observe the sky for years and never see another burst from the same location. But certain sources refused to follow that pattern. They erupted, then erupted again and again. The same region of the sky, the same source, multiple bursts. That repetition immediately caught researchers' attention, because repetition implied survival. A typical gamma-ray burst destroys or fundamentally transforms whatever created it. A repeating source suggests the object remains intact afterward. Something was producing bursts and living to do it again. That was unusual. Imagine hearing an explosion in the distance. A few days later, another explosion occurs from exactly the same place, then another. Eventually you'd start wondering what sort of operation was running out there. Astronomers found themselves asking essentially the same question. The first recognized soft gamma repeater was identified in the late 1970s. The object would eventually receive the somewhat elegant name SGR 0526-66. Like many astronomical names, it sounds less like a cosmic wonder and more like a password someone forgot to write down. Scientists are often remarkably practical when naming things. The source was located near the remnants of a supernova in the Large Magellanic Cloud, a neighbouring galaxy orbiting the Milky Way. Then came an extraordinary event. On March 5th, 1979, detectors recorded one of the most remarkable bursts ever observed. The flash was powerful, extremely powerful, and unlike conventional gamma-ray bursts, it displayed characteristics that seemed entirely different. The event lasted longer than expected. Its structure was unusual, and perhaps most importantly, the source eventually produced additional bursts. Astronomers suddenly had evidence that some gamma-ray emitters could repeat. That discovery opened an entirely new branch of investigation. At first, nobody knew whether these repeating sources represented a rare variation of known phenomena or something completely new. The answer required patience. Astronomy often rewards patience. The universe rarely rushes explanations. Years passed. More observations accumulated. Additional repeating sources appeared. Patterns emerged. The bursts shared similarities. They tended to originate within our galaxy or nearby regions rather than from the distant universe. Their energies differed from traditional gamma-ray bursts. Their behavior differed. Their repetition differed. Slowly, a new category began taking shape. Researchers eventually coined the term soft gamma repeater. The name reflected the observations. The burst consisted of relatively lower energy gamma rays compared with some other gamma ray events. They repeated. Therefore, soft gamma repeater. Not a flashy name, not a dramatic name, but accurate. Astronomers generally prioritize accuracy over marketing. Meanwhile, the mystery deepened. Every new observation raised additional questions. Why did these bursts occur? What powered them? Why did they repeat? What kind of object could survive repeated eruptions? The data painted an increasingly strange picture. The bursts were brief. Some lasted less than a second. Yet during those fractions of a second, enormous amounts of energy were released. Then silence returned. Days might pass. Months might pass. Years might pass. Nothing happened. Then another burst would arrive unexpectedly. It was as though these objects spent most of their existence sleeping before occasionally waking up and shouting across the galaxy. Researchers searched for clues. The locations of several soft gamma repeaters proved particularly revealing. Many appeared associated with supernova remnants. This connection mattered. Supernova remnants are the expanding clouds of gas left behind when massive stars explode. Finding SGRs near such remnants suggested a relationship. Perhaps these mysterious sources were somehow connected to stellar death. That realization narrowed the field considerably. If soft gamma repeaters emerged from supernova explosions, then neutron stars became obvious suspects. After all, neutron stars are among the most common remnants left behind by massive stars. The idea made sense. Neutron stars were compact, energetic, capable of producing high-energy radiation. Yet there remained a problem. Ordinary neutron stars didn't behave like soft gamma repeaters. Pulsars produced regular emissions. They didn't typically unleash sudden gamma-ray explosions. Something else seemed necessary. Something more extreme. As the 1980s and 1990s progressed, evidence gradually accumulated in favor of a remarkable possibility. The repeating sources might be associated with neutron stars possessing extraordinarily powerful magnetic fields. Theoretical work suggested such objects could exist. Observational evidence increasingly pointed in the same direction. Eventually the pieces began fitting together. The bursts, the repetition, the locations near supernova remnants, the energy output. Everything started aligning around a single explanation. Magnetars. The proposal was both elegant and unsettling. Imagine a neutron star with a magnetic field so powerful that it stores staggering amounts of energy. Over time, stresses develop within the star. The magnetic field twists and evolves. Eventually something gives way. Energy is released. A burst occurs. The star survives. The cycle repeats. For the first time, astronomers possessed a framework capable of explaining the observations. Not every detail, not every mystery, but enough to make sense of the overall behavior. The discovery represented a significant milestone, yet perhaps the most dramatic moment arrived years later. On August 27, 1998, a magnetar known as SGR 1900+14 produced an enormous flare. The event was so powerful that instruments across Earth and in orbit detected it easily. For a brief period, a dead star located roughly 20,000 light-year away became one of the most noticeable objects in the high-energy sky. Then it happened again. In December 2004, another magnetar generated what remains one of the most powerful bursts ever recorded from outside the solar system. The source was SGR 1806-20. The flare was astonishing. For a fraction of a second, it released more energy than our sun produces over hundreds of thousands of years. Think about that for a moment. A dead stellar remnant roughly the size of a city briefly outperformed a star containing more than 300,000 Earth masses. The event occurred approximately 50,000 light-years away. Yet despite that enormous distance, its effects were measurable on Earth. Our atmosphere responded. Satellites noticed. Instruments recorded the disturbance. That's how powerful the flare was. If it had occurred much closer, the consequences might have been significantly more dramatic. Fortunately, 50,000 light-years provides a very comfortable safety margin. The universe occasionally reminds us to appreciate distance. These giant flares transformed soft gamma repeaters from scientific curiosities into some of the most fascinating objects in astrophysics. They demonstrated beyond doubt that extraordinary amounts of energy remain trapped inside these remnants. The challenge shifted from discovery to understanding. Researchers now knew the objects existed. They knew the bursts were real. They knew magnetars likely played a central role. The next step involved figuring out precisely how such eruptions occurred. What mechanism released the energy? Why were some bursts small while others became enormous? What happened inside these compact stellar remnants before an eruption? By this point in our journey, we've encountered a peculiar group of objects. We've seen that massive stars can die in spectacular supernova explosions. We've learned that those explosions sometimes leave behind neutron stars, objects so dense and compact that they challenge common sense. And we've followed astronomers as they gradually uncovered mysterious sources that repeatedly unleashed bursts of gamma radiation from fixed locations in the sky. Now it's time to answer a question that has quietly followed us through the story so far. What exactly is a soft gamma repeater? The name appears straightforward enough. 3 words: soft gamma repeater. Yet each part carries a surprising amount of meaning. And as is often the case in astronomy, the name tells us what scientists first observed, not necessarily what the object truly is. To understand why, let's start with the middle word, gamma. Gamma rays represent the most energetic form of electromagnetic radiation. Everything around us exists within the electromagnetic spectrum. Radio stations broadcast radio waves. Microwave ovens use microwaves. Remote controls often rely on infrared light. Our eyes detect visible light. Sunburns come from ultraviolet radiation. Medical imaging can involve X-rays. Beyond all of those lie gamma rays. If visible light were a piano keyboard, gamma rays would be the highest notes imaginable. They carry enormous amounts of energy. They emerge from some of the most extreme environments in the universe: black holes, supernovae, neutron stars, colliding stellar remnants. Whenever astronomers detect gamma rays, they immediately know something unusual is happening. The universe does not casually produce gamma radiation. It's generally a sign that physics is working overtime. This was one reason the original discoveries attracted so much attention. The bursts being detected weren't ordinary flashes of light. They belonged to the most energetic category available. Something powerful was occurring. Something capable of producing radiation that would never naturally reach Earth's surface because our atmosphere blocks it. Fortunately. Because while gamma rays are fascinating scientifically, they're considerably less appealing biologically. Most forms of life prefer not being bombarded by intense gamma radiation. It's one of many reasons we owe a quiet thank you to our atmosphere. Now let's examine the first word: soft. At first glance, this seems oddly chosen. Nothing about gamma rays sounds soft. Nothing about exploding stellar remnants sounds soft. Nothing about neutron stars sounds soft. So why use the term? In astronomy, soft has a specific meaning. It does not mean gentle. It does not mean harmless. It does not mean relaxing. Instead, it refers to energy. Compared to certain other gamma ray phenomena, the radiation emitted by these objects contains somewhat lower energy gamma rays. They're still extraordinarily energetic by everyday standards. They're simply less energetic than some of the most extreme gamma ray bursts known. It's a bit like comparing hurricanes. One storm might be less powerful than another, while still being perfectly capable of ruining your weekend. The label is relative. Soft gamma repeaters emit gamma rays that are softer than some alternatives, not soft in any ordinary human sense. Astronomers have a long tradition of using words in ways that occasionally confuse everyone else. This is one of those cases. That leaves us with the final word, repeater. And in many ways, this is the most important part of the name, because repetition is what made these objects so surprising in the first place. Traditional gamma-ray bursts generally occur once. A catastrophic event happens, a burst is released. The source changes fundamentally or disappears entirely. Astronomers move on. Soft gamma repeaters refuse to cooperate with that pattern. They erupted repeatedly. The same source, the same object. Multiple bursts over time. That repetition immediately suggested something important. Whatever produced the bursts survived them. Imagine watching a firecracker explode. Afterward, there is no firecracker left. The event consumes the object. Now, imagine the same firecracker exploding every few weeks for years. Clearly something different is happening. That was the mystery astronomers faced. The source wasn't destroying itself. It was releasing energy while remaining intact. Again and again. Over years, sometimes decades. And that meant scientists weren't dealing with a one-time catastrophe. They were dealing with an ongoing process, something capable of repeatedly storing and releasing enormous amounts of energy. Eventually the evidence became overwhelming. Soft gamma repeaters were not a separate category entirely. They belonged to a larger family. The family of magnetars. Today, astronomers generally view soft gamma repeaters as magnetars displaying a particular kind of activity. In other words, the name describes behavior rather than identity, a bit like calling someone a runner. The word tells you what they do, not necessarily everything they are. A soft gamma repeater is essentially a magnetar that produces repeated bursts of gamma radiation. Simple definition. Extraordinary object. To appreciate how remarkable this is, consider the scale involved. A magnetar may contain more mass than our Sun. Its diameter might be only 20 kilometers. Its magnetic field can be trillions of times stronger than Earth's, and somehow this compact object stores enough energy to generate bursts detectable across vast regions of the galaxy. The numbers quickly become difficult to visualize, so let's approach the problem differently. Imagine compressing an entire mountain range into a single marble, then giving that marble one of the strongest magnetic fields in the universe, then placing it thousands of light years away. Even after all that distance, its occasional outbursts remain visible to scientific instruments orbiting Earth. That's roughly the situation astronomers are dealing with. The bursts themselves vary considerably. Most are relatively brief. Some last only fractions of a second. A sudden flash appears, energy is released, then silence returns. Others continue for several seconds. A few become dramatically larger. These giant flares represent some of the most energetic events associated with magnetars. The difference between an ordinary burst and a giant flare can be enormous. It's somewhat like comparing a camera flash to a stadium floodlight. Both produce light. The scale is entirely different. One of the interesting features of the soft gamma repeaters is their unpredictability. Astronomers cannot reliably predict exactly when a burst will occur. The objects may remain quiet for long periods. Then activity suddenly increases. Several bursts might occur over a short interval. Then calm returns. Researchers sometimes refer to these active periods as burst storms. The term is quite fitting. A magnetar may spend years appearing relatively peaceful. Then it enters a period of heightened activity during which numerous bursts occur. Eventually the storm passes. The star settles down once more, at least until the next episode. This unpredictability made early observations especially challenging. Imagine trying to study thunderstorms if storms happened only every few years and lasted mere seconds. You would need patience. Lots of patience. Astronomers developed plenty of it. Fortunately, modern instruments continuously monitor large portions of the sky. When a burst occurs, satellites can detect it almost immediately. Observatories around the world can respond quickly. Data begins flowing. Scientists start analysing. The process has become remarkably efficient. Yet despite decades of study, soft gamma repeaters remain fascinating precisely because they continue surprising researchers. Every so often a burst arrives that behaves slightly differently. A flare exceeds expectations. A new source appears. Another clue emerges. The story keeps evolving. One reason these objects generate such excitement is that they allow scientists to investigate physics under conditions impossible to recreate on Earth. Even our most advanced laboratories fall far short of magnetar environments. We can generate powerful magnetic fields. Magnetars generate incomparably stronger ones. We can study dense matter. Magnetars contain matter compressed beyond anything achievable in terrestrial experiments. We can model extreme gravity. Magnetars live inside it. In a sense, every soft gamma repeater functions as a natural laboratory, a place where the laws of physics operate under extraordinary conditions. And because these objects occasionally announce their activity through bursts, astronomers gain opportunities to observe those conditions in action. The bursts themselves are not random. They reveal information. Their duration matters. Their energy matters. Their timing matters. Their structure matters. Every eruption contains clues about what is happening inside the star. Researchers analyze those clues carefully. Patterns emerge. Models improve. Understanding gradually increases. One of the most significant realizations involved the source of the energy. Early on, astronomers considered several possibilities. Perhaps rotation powered the bursts. Perhaps accretion played a role. Perhaps some unknown process was involved. Over time, evidence increasingly favored magnetic energy, specifically the enormous magnetic energy stored within magnetars. This was a profound insight. For most stars, energy comes from fusion. Hydrogen becomes helium. Energy is released. Simple. Magnetars operate differently. Their bursts originate not from ongoing fusion, but from magnetic fields. Fields so powerful that they contain staggering amounts of stored energy. That energy can be released suddenly, violently, repeatedly. Which brings us back to the original mystery. Why do these dead stars keep exploding? The answer is that they aren't really exploding in the conventional sense. The star itself isn't being destroyed each time. The bursts represent energy releases. Magnetic events. The stellar equivalent of tension suddenly giving way. A useful comparison might be an earthquake. When an earthquake occurs, Earth does not explode. Stress accumulates within the planet's crust. Eventually something shifts. Energy is released. The planet survives. The cycle continues. As astronomers began studying magnetars more closely, they realized something similar might be happening. Stress accumulates. The magnetic field evolves. The star's crust experiences strain. Eventually something gives way, a burst follows, the object survives, and the process can happen again. This framework elegantly explains the repetition. The bursts aren't isolated events. They're symptoms of an ongoing physical process, a process capable of operating for thousands or even tens of thousands of years, a process driven by some of the strongest magnetic fields known in nature. If magnetic fields are responsible, just how powerful must those fields be? How can magnetism alone generate such extraordinary outbursts? And what exactly makes a magnetar different from an ordinary neutron star? Not every record in the universe is easy to appreciate. Take speed. Everyone understands why the fastest runner matters. Take size. The tallest mountain or largest ocean naturally captures attention, but magnetism is different. Most of us go through our daily lives barely thinking about magnetic fields at all. They're quietly present in the background. Your phone relies on them. Your speakers rely on them. Compasses rely on them. Earth itself is wrapped in a magnetic field that helps protect us from charged particles arriving from space. Yet because magnetism is invisible, it rarely receives the same attention as gravity, light, or motion. That's understandable. After all, nobody looks up at the night sky and immediately says, "What an impressive magnetic field!" And yet, hidden among the stars are objects that have turned magnetism into something so extreme that it becomes the dominant force in their existence. Objects whose magnetic fields are not merely strong, not merely powerful, but so overwhelmingly intense that they fundamentally reshape the physics occurring around them. These objects are called magnetars, and without them, soft gamma repeaters would remain one of astronomy's greatest mysteries. Because over time, astronomers came to realize something remarkable. The bursts weren't coming from ordinary neutron stars. They were coming from neutron stars whose magnetic fields had become so powerful that they represented an entirely separate category of object. The difference is difficult to exaggerate. Even among neutron stars, magnetars are exceptional. To understand why, let's start somewhere familiar. Earth possesses a magnetic field. It's generated deep within our planet by the motion of molten iron in the outer core. That field extends far into space, creating a protective bubble known as the magnetosphere. Without it, life on Earth would face a constant bombardment of charged particles from the Sun. Solar storms would have much more dramatic consequences. Our atmosphere would gradually suffer greater erosion. The world would be a considerably harsher place. Most of the time, Earth's magnetic field quietly does its job without demanding attention. Occasionally, however, it reveals itself through phenomena like the aurora. Charged particles from space interact with the atmosphere, producing shimmering curtains of light near the poles. Beautiful, elegant, and ultimately powered by magnetism. Earth's magnetic field is strong enough to guide compasses and protect a planet. That sounds impressive. Until you compare it with a refrigerator magnet. A typical refrigerator magnet can actually produce a stronger local magnetic field than Earth itself. Not over large distances, of course, but right at its surface. The comparison often surprises people. Earth feels enormous. The refrigerator magnet feels trivial, yet magnetism doesn't always follow our intuitions. Now let's scale upward. Hospitals use MRI machines capable of generating magnetic fields thousands of times stronger than Earth's. These machines are extraordinary pieces of engineering. They allow doctors to see inside the human body without surgery. They represent some of the strongest magnetic fields routinely encountered by people. Stand near an MRI machine and safety rules become very important. Metal objects must be carefully controlled. Equipment must be specifically designed. Magnetic forces become impossible to ignore. For most practical purposes, MRI machines seem incredibly powerful. Then neutron stars arrive and ruin everyone's sense of scale. A typical neutron star possesses a magnetic field billions, or even trillions of times stronger than Earth's. Even ordinary neutron stars operate in a realm almost impossible to comprehend. Imagine taking every magnet you've ever encountered, every refrigerator magnet, every compass, every laboratory magnet, every industrial electromagnet, combine them all, multiply their strength again and again and again. You still wouldn't be close. Neutron stars simply inhabit a different universe of magnetism. Yet magnetars go further, much further. A magnetar's magnetic field can be 1,000 times stronger than that of a typical neutron star. And since ordinary neutron stars are already absurdly magnetic, that additional factor pushes things into territory that feels almost unreasonable. Scientists estimate that magnetars possess magnetic fields reaching around 1 quadrillion Gauss. A quadrillion! That's a 1 followed by 15 zeros. Numbers this large become difficult to visualize. Human intuition generally gives up somewhere around a few million. Beyond that, we mostly rely on comparisons, so let's use one. If Earth was somehow moved dangerously close to a magnetar, the consequences would begin long before the star itself became visible. At a distance of hundreds of thousands of kilometers, The magnetic field could interfere with electronic systems. Closer still, the effects become increasingly dramatic. The magnetic forces could distort atomic structures. Chemical bonds might be altered. Matter itself would behave differently. Fortunately, no known magnetar exist anywhere near Earth. The nearest known examples remain comfortably distant. Cosmic distances occasionally feel inconvenient to astronomers. In this case, they're quite reassuring. The obvious question is why? Why do magnetars possess such extreme magnetic fields? What makes them different from ordinary neutron stars? The answer begins during the violent final moments of a massive star's life. As we've already discussed, when a massive star dies, its core collapses. The collapse happens rapidly. A region once thousands of kilometers across shrinks to roughly 20 kilometers. That's an extraordinary reduction in size. And whenever something shrinks dramatically while preserving certain physical properties, interesting things happen. Imagine stretching a rubber band around a large beach ball. Now deflate the ball until it's the size of a marble. The rubber band becomes concentrated into a much smaller space. Something similar occurs with magnetic fields during stellar collapse. The magnetic field lines become compressed. Their strength increases dramatically. At the same time, the star's rotation speeds up. The combination can generate astonishing magnetic intensities. Not every neutron star becomes a magnetar. Scientists are still investigating exactly why some develop especially powerful fields while others do not. The details remain an active area of research. But under the right conditions, the collapsing star appears capable of generating one of the strongest magnetic fields found anywhere in nature. Once formed, the magnetar enters a remarkable phase of existence. Unlike ordinary stars, it is no longer powered by nuclear fusion. Its stellar life has ended. No hydrogen is being converted into helium. No vast fusion furnace remains active. And yet the object still contains enormous amounts of energy. That energy resides within the magnetic field itself. This is a crucial point. When astronomers first encountered soft gamma repeaters, they faced a puzzle. Where was the energy coming from? Traditional stars derive energy from fusion. Black holes derive energy from gravity and accretion. What powered repeated gamma-ray bursts from apparently dead stellar remnants? Magnetars provided the answer. The magnetic field itself functions as a colossal energy reservoir. Imagine stretching an elastic band. The more you stretch it, the more energy becomes stored. Release the tension, and that energy emerges. Now imagine an elastic band the size of a star. Then increase its stored energy beyond anything humans can realistically comprehend. That's roughly the role played by a magnetar's magnetic field. Of course, magnetic fields are not literal elastic bands, but the analogy helps capture the basic idea. Energy becomes stored, stress develops. Eventually that stress can be released, and when it is released, extraordinary things happen. For years, astronomers attempted to understand precisely how magnetars produce their bursts. The answer gradually emerged from observations and theoretical models. The magnetic field is not perfectly stable. It evolves over time, it twists, it shifts, it rearranges itself, and as it does so, enormous stresses build within the star. Imagine tectonic plates on Earth. They move slowly. Stress accumulates. Eventually a fault slips. An earthquake occurs. Energy is released. The process then begins again. Scientists began realizing that something broadly similar might happen within magnetars. The magnetic field exerts immense forces on the star's crust. Over time, those forces build tension. Eventually the crust can no longer withstand the stress. Something cracks, something shifts, and a tremendous burst of energy erupts into space. This framework elegantly explained many observations. The bursts weren't random explosions, they were consequences of magnetic stress. The magnetar wasn't coming back to life, it wasn't reigniting fusion. Instead, it was releasing energy stored within its magnetic field. That realization transformed magnetars from interesting curiosities into central players in high-energy astrophysics. They became laboratories for studying physics under conditions unavailable anywhere else. The magnetic fields involved are simply too extreme to reproduce on Earth. Even our most powerful facilities fall unimaginably short. As a result, every magnetar offers a unique opportunity. Researchers can observe how matter behaves under extraordinary magnetic pressure. They can test theories about dense stellar remnants. They can investigate the relationship between magnetism and high-energy radiation. Each burst becomes a source of information. Each flare becomes a clue, and some clues proved especially dramatic. As astronomers monitored magnetars over the years, they occasionally witnessed giant flares. These events make ordinary bursts look modest. For a brief moment, a magnetar can release more energy than the sun emits in hundreds of thousands of years. That statement almost sounds like a mistake, yet observations confirm it. A dead star roughly the size of a city briefly outshining expectations by enormous margins. The most famous giant flare occurred in December 2004. The source was SGR 1806-20. Located approximately 50,000 light-years away, it produced an eruption so powerful that instruments detected measurable effects on Earth's atmosphere. Pause for a moment and consider that. 50,000 light-years. Light itself requires 50,000 years to cross that distance. Human civilization has changed beyond recognition in merely a few thousand years, and yet an event occurring that far away still managed to leave detectable fingerprints here. The scale involved is extraordinary. Fortunately, distance once again protected us. Had the same flare occurred much closer, the consequences could have been far more significant. Fortunately, the galaxy is large, very large, and magnetars tend to keep their distance. Still, those giant flares revealed something important. The magnetic fields weren't merely strong, they contained truly staggering amounts of stored energy. Enough energy to explain soft gamma repeater activity. Enough energy to explain repeated eruptions. Enough energy to transform our understanding of what dead stars could do. By this stage, astronomers had largely solved one major mystery. The repeaters were magnetars. The bursts were powered by magnetic energy. The extraordinary fields explained the observations. If magnetic stress builds within these stars, exactly what happens when the pressure becomes too great? What physical event triggers the bursts? How does a magnetic field cause a dead star to erupt? Consider the strongest earthquake you have ever heard about. Perhaps you've seen footage of buildings shaking, roads splitting, or entire landscapes shifting over the course of a few terrifying seconds. Earthquakes remind us that even something as seemingly solid and permanent as a planet is not entirely stable. Beneath our feet, enormous forces are constantly at work. Most of the time those forces remain hidden. Then pressure builds, stress accumulates. Eventually something gives way, the ground moves, energy is released, and the planet briefly reminds everyone that it is still very much alive. Now imagine an earthquake occurring on an object no larger than a city. Imagine that object contains more mass than the sun. Imagine gravity so strong that matter itself exists in forms unknown anywhere on Earth. Imagine magnetic fields powerful enough to distort atoms. Then take the largest earthquake in human history and make it look insignificant by comparison. Welcome to the world of starquakes. If magnetars are the most magnetic objects known, then starquakes are among their most dramatic behaviours. And according to current scientific understanding, starquakes are responsible for many of the bursts we observe from soft gamma repeaters. The idea sounds almost poetic at first, a dead star cracking, a stellar earthquake. But the reality is neither poetic nor gentle. It is physics operating at some of the most extreme limits nature allows. To understand why starquakes happen, we first need to examine something surprising. Despite their incredible density, Neutron stars are not completely uniform spheres of fluid. They possess structure, layers, regions with different physical properties. In some ways, they resemble planets more than many people realize. Not in composition, of course. A neutron star is nothing like Earth, but like Earth, it has an outer region and an interior, and that outer region behaves in fascinating ways. The surface of a neutron star is often described as a crust. The word crust may sound ordinary. Perhaps it brings to mind the crust of Earth, or bread, or the slightly burnt edge of a pizza. Neutron star crusts are somewhat less approachable. They are believed to consist of densely packed atomic nuclei, arranged in structures unlike anything naturally found on our planet. The material is incredibly rigid. In fact, scientists think neutron star crusts may be among the strongest materials in the universe. Not strong compared to steel, not strong compared to diamonds, strong compared to anything, period. If you could somehow transport a piece of neutron star crust to Earth while preserving its structure, it would possess incredible strength. Again, practical difficulties make such experiments unlikely. Astronomy frequently presents us with fascinating materials located impossibly far away. Still, theoretical calculations suggest that neutron star crusts are extraordinarily tough, which is fortunate, because they endure unimaginable stresses. Those stresses come primarily from the magnetic field. As we discussed previously, magnetars possess magnetic fields of astonishing intensity. But magnetic fields are not static. They evolve, they shift, they twist. And when they twist, they exert forces on the crust. Imagine bending a metal ruler. At first the ruler resists, the material flexes slightly, pressure builds. If you continue applying force, eventually the ruler snaps. The break occurs suddenly. Energy that was stored within the bent ruler is released. Something broadly similar appears to happen inside magnetars. Over time, the magnetic field slowly changes. As it changes, it places increasing stress on the crust. The crust resists. For years, decades, perhaps centuries. Pressure continues building. Then eventually the material reaches its limit. A fracture occurs. A shift takes place. The crust suddenly rearranges itself. And an enormous amount of energy is released. That event is what astronomers call a starquake. The name is appropriate. The process shares important similarities with earthquakes. In both cases, stress accumulates gradually. In both cases, rigid material eventually fails. In both cases, energy is released suddenly. The difference lies in scale. Earthquakes involve rock. Starquakes involve matter compressed under conditions so extreme that normal intuition becomes unreliable. Earthquakes release energy measured in familiar units. Starquakes can release enough energy to outshine entire galaxies for brief periods. The comparison quickly becomes unfair to Earth. Our planet simply isn't playing the same game. One way to appreciate the difference is to examine the largest earthquake ever recorded. The Great Chilean Earthquake of 1960 reached a magnitude of approximately 9.5. It released enormous amounts of energy. Entire regions were affected, tsunamis crossed oceans. The event remains one of the most powerful geological disasters in recorded history. Yet compared with a major magnetar starquake, it barely registers. The energy released during some soft gamma repeater bursts exceeds the output of countless terrestrial earthquakes combined. Not because the crust is larger, quite the opposite. A neutron star is tiny compared to a planet, but the forces operating inside it are vastly greater. Gravity is stronger, density is greater, magnetic fields are incomparably more intense. Everything is pushed to extremes. As astronomers developed models of magnetars, they realized starquakes could naturally explain several observed features. Most importantly, they explained repetition. A supernova happens once, a starquake can happen many times. This distinction matters enormously. The original mystery surrounding soft gamma repeaters was never simply the bursts themselves. It was the fact that they kept happening, again and again. The source survived. The process repeated. Starquakes offered exactly that kind of mechanism. Stress builds, the crust cracks, energy is released, the star survives. Then the cycle begins anew, simple in principle, extraordinary in practice. Interestingly, not every starquake produces the same result. Some are relatively modest, others are spectacular. The smallest events generate short bursts lasting fractions of a second. These are the most common observations associated with soft gamma repeaters. A brief flash appears, detectors register the burst, then everything returns to normal, at least temporarily. Larger starquakes create stronger eruptions, and under certain circumstances truly enormous events occur. These giant flares represent the most dramatic expressions of magnetar activity. To understand why, imagine stretching a rubber band. A small stretch stores a little energy, a larger stretch stores more. The amount of released energy depends on how much tension existed beforehand. Similarly, larger magnetic distortions can store larger amounts of energy. When those distortions suddenly reorganize, the resulting flare becomes correspondingly more powerful. Scientists sometimes compare the process to solar flares. The comparison isn't perfect, but it helps. The Sun also possesses magnetic fields. Solar flares occur when magnetic field lines become tangled and suddenly reconnect. Energy is released, particles accelerate, radiation floods into space. Magnetars appear capable of something conceptually similar. The difference is that magnetars operate under conditions millions or billions of times more extreme. It's the same basic story written with much larger numbers, and the universe, as we've learned repeatedly, is very fond of large numbers. One fascinating aspect of starquakes involves vibrations. When a major earthquake occurs on Earth, the planet literally vibrates. Seismic waves travel through the interior. Sensitive instruments detect those waves. Scientists learn about Earth's structure by studying them. Magnetars appear to behave similarly. After major starquakes, researchers have detected oscillations in the emitted radiation, tiny rhythmic patterns, subtle fluctuations, evidence that the entire neutron star may be vibrating. Think about that for a moment. An object containing more mass than the Sun, an object only 20 kilometers across, an object with one of the strongest magnetic fields in existence, ringing like a bell. Not a musical bell, of course, a cosmic bell, a stellar bell. A dead star trembling after its crust has cracked. The idea sounds almost fictional, yet observations support it. These vibrations provide valuable information. By studying them, astronomers can learn about the internal structure of neutron stars. It's a bit like tapping a wall to determine what's behind it. The sound reveals clues. The vibrations reveal structure. Except in this case, the wall happens to be thousands of light years away and made of neutron-degenerate matter. Astronomy occasionally complicates otherwise straightforward techniques. As exciting as starquakes are scientifically, they also solved another important problem. They explained why soft gamma repeaters can remain dormant for long periods. If bursts required continuous activity, we would expect constant emissions. Instead, magnetars often spend years appearing relatively quiet. That behaviour makes sense if stress accumulation is part of the process. Earthquakes don't occur continuously. Pressure requires time to build. The same principle applies here. A magnetar may spend years accumulating magnetic stress. Nothing dramatic happens. Then suddenly a fracture occurs. A burst follows. The star settles. The cycle repeats. This framework transforms soft gamma repeaters from mysterious curiosities into understandable physical systems, complex systems, extreme systems. But understandable. Scientists now possessed a coherent explanation linking observations to theory. The bursts originated from magnetars. The energy came from magnetic fields. The immediate trigger involved starquakes and magnetic rearrangements. The pieces fit together remarkably well. There are moments in astronomy when numbers become almost useless, not because the numbers are inaccurate, not because scientists made mistakes, but because the scale involved becomes so enormous that human intuition simply refuses to cooperate. 1 billion is already difficult to picture. 1 trillion is worse. By the time astronomers start discussing the energy released by magnetars, most people's internal measuring systems have quietly packed their bags and gone home. And yet, every now and then, the universe provides a real-world demonstration. A moment when an event occurring tens of thousands of light years away produces effects that can actually be measured here on Earth. Those moments force us to confront a remarkable reality. Some of the dead stars scattered throughout our galaxy are far more powerful than they appear. The most dramatic example arrived near the end of 2004. At first, nobody on Earth noticed anything unusual. People went to work, students attended school, planes crossed the sky, cities hummed with activity. The world continued exactly as it always had. Then, 50,000 light years away, a magnetar experienced one of the most violent outbursts ever observed. The object was known as SGR 1806-20. At the time, astronomers already knew it was unusual. They knew it belonged to the family of soft gamma repeaters. They knew it occasionally produced bursts. What they didn't know was that it was about to provide one of the most astonishing demonstrations of magnetic power ever recorded. The event occurred on December 27th, 2004. For a fraction of a second, SGR 1806-2 unleashed a giant flare of extraordinary intensity. The burst lasted only a brief moment, yet during that brief moment, it became one of the brightest events ever detected from outside our solar system. The phrase giant flare sounds almost modest. It sounds like something that might happen on the sun. Perhaps a larger than usual solar eruption. A bit dramatic, certainly, but manageable. The reality was considerably more impressive. To appreciate the scale, imagine every power station on Earth operating simultaneously. Every wind turbine, every solar panel, every hydroelectric dam, every nuclear reactor, every coal plant, every generator. Now add all of that together. The result is still insignificant compared to the energy released during the giant flare. In fact, humanity's total energy production barely qualifies as a rounding error when discussing events of this magnitude. The magnetar released more energy in a fraction of a second than our civilization could produce over unimaginably long periods, and that was just the beginning. Astronomers estimate that the flare emitted more energy in a single tenth of a second than the Sun produces in roughly 100,000 years. Pause for a moment and consider that comparison. The Sun is not exactly lazy. Every second it converts hundreds of millions of tons of hydrogen into helium. Every second it radiates enormous amounts of energy across the solar system. It powers climates, drives weather, supports ecosystems, keeps entire planets warm. The Sun works continuously, without interruption, day after day, year after year, century after century. Yet this dead star briefly matched what our Sun would produce over 100 millennia, and it accomplished that feat in less time than it takes to blink. This is where astronomy becomes wonderfully unreasonable. The numbers stop feeling real. The universe starts behaving like an enthusiastic storyteller who has forgotten the concept of moderation. Yet every measurement confirmed the event. Every observation supported the conclusions. The flare was real, the energy was real, the implications were real. Perhaps the most remarkable part of the story is that Earth noticed. Remember the distance involved. 50,000 light years. Light itself requires 50,000 years to travel from the source to us. When the flare occurred, humanity was receiving energy that had begun its journey long before agriculture existed, long before cities, long before writing, long before civilization itself. And despite crossing such unimaginable distances, enough energy remained for measurable effects to occur here. The burst ionized portions of Earth's upper atmosphere. Instruments detected changes. Satellites recorded disturbances. The event literally altered conditions around our planet. Not dramatically, not dangerously, but measurably. That fact alone is astonishing. Most objects 50,000 light-years away are so distant that their influence on Earth is effectively non-existent. A magnetar giant flare is different. For a brief moment it announces its presence across the galaxy. Astronomers sometimes joke that the universe occasionally taps us on the shoulder. This was less of a tap, and more of a very energetic wave from across town. The event immediately became one of the most important observations in magnetar research. Scientists now had direct evidence that these dead stars could produce eruptions of almost unimaginable power. And naturally a question followed. What would happen if such an explosion occurred closer? This is where things become particularly interesting. Fortunately, there are no known magnetars dangerously near Earth. The closest known examples remain at safe distances. Very safe distances. The galaxy is enormous, space is mostly empty, and that emptiness works in our favour. Still, astronomers enjoy thought experiments. They're useful tools for understanding scale. So let's imagine a magnetar much closer than SGR 1806-20. Not nearby enough to pose an immediate threat, just close enough to illustrate the physics. Suppose such an event occurred a few thousand light-years away rather than 50,000. The flare would appear significantly brighter. Its effects on Earth's atmosphere would be stronger. Communication systems might experience disruptions. Satellites could face increased radiation exposure. Scientists would become very busy very quickly. Move the source even closer. The consequences become more serious. At sufficiently short distances, a giant flare could potentially damage portions of the ozone layer. The increased radiation exposure would create challenges for life on Earth's surface. Fortunately, no known magnetar occupies such a position, and the odds of an appropriately timed giant flare occurring at exactly the wrong distance remain very low. Astronomy occasionally produces frightening scenarios. This is not generally considered one of humanity's immediate concerns. Asteroids rank much higher on the list. Still, the exercise demonstrates something important. These explosions are not merely large by astronomical standards. They are genuinely powerful. Powerful enough that distance becomes our primary protection. And distance, fortunately, is something the universe provides in abundance. The 2004 giant flare was not unique. Other magnetars have produced similar events. One particularly famous example occurred in 1998. The source was SGR 1900+14. Again, astronomers observed an eruption of extraordinary power. Again, instruments detected the burst across vast distances. Again, researchers gained valuable information about the behaviour of magnetars. Each giant flare helps refine our understanding. Each observation provides new clues. Each event reveals another piece of the puzzle. What's especially fascinating is that giant flares appear to occur in stages. The initial flash is typically the most intense. A tremendous burst of gamma rays erupts outward. Then comes a longer-lasting tail of radiation. This tail often displays periodic variations linked to the rotation of the neutron star. Imagine a cosmic lighthouse whose beam has suddenly become unimaginably bright. As the star rotates, astronomers observe rhythmic changes in the emitted radiation. These patterns help researchers study the object's properties, its rotation rate, its magnetic field, its structure. Even during explosive outbursts, the magnetar continues teaching scientists about itself. One of the reasons these events generate so much excitement is that they provide direct evidence of the enormous energy stored within magnetic fields. That statement may sound obvious after several sections discussing magnetars, yet it remains one of the most remarkable conclusions in modern astrophysics. Most people think of magnetic fields as subtle influences, useful for navigation, useful for technology. Useful for sticking grocery lists to refrigerators, magnetars reveal a completely different side of magnetism. Under the right conditions, magnetic fields become vast reservoirs of energy capable of rivaling stellar processes, energy capable of producing bursts visible across galaxies, energy capable of shaking Earth's atmosphere from 50,000 light-years away. The realization transformed how scientists viewed these objects. Originally, astronomers searched for explanations involving traditional energy sources, fusion, accretion, rotation. Over time, evidence increasingly pointed elsewhere. The magnetic field itself became the answer, not a supporting factor, not a secondary influence, the primary engine. That conclusion solved many mysteries. It explained the bursts, it explained the repetition, it explained the giant flares. Most importantly, it explained why dead stars could remain active long after their stellar lives ended. The magnetar wasn't alive in the traditional sense. Fusion had stopped. The star's original energy source was gone, yet immense magnetic energy remained, and that energy continued reshaping the star's behaviour. There's something slightly ironic about the situation. When people imagine stellar death, they usually picture stillness, silence, a gradual fading into darkness. Magnetars refuse to cooperate with that image. They remain dynamic, restless, occasionally explosive. Even after death, they continue influencing their surroundings. They continue evolving. They continue surprising astronomers. In many ways, giant flares represent the ultimate expression of that restlessness. A sudden reminder that beneath the surface of these compact remnants, extraordinary forces remain at work. For a fraction of a second, the stored magnetic energy erupts outward. Then calm returns, the star survives, the cycle continues, and that survival may be the most fascinating aspect of all. Imagine a conventional explosion powerful enough to release such enormous energy. You would expect devastation, destruction, fundamental change. Yet magnetars endure. The burst occurs, the flare fades, the object remains, ready to continue accumulating stress, ready to continue evolving, ready eventually to produce future eruptions. The giant flare of 2004 revealed this resilience dramatically. Despite releasing astonishing amounts of energy, SGR 1806-20 survived. The magnetar remained intact. The process continued. The dead star lived on. Or perhaps more accurately, the dead star continued refusing to stay quiet. By now, astronomers had assembled a fairly coherent picture. Massive stars die. Neutron stars form. A small fraction become magnetars. Magnetic stresses build. Starquakes occur. Bursts emerge. Occasionally, giant flares erupt with enough energy to affect Earth from across the galaxy. The framework worked remarkably well, yet another intriguing question remained. If magnetars are capable of such extraordinary behaviour, what would it actually be like to exist near one? How would a nearby magnetar affect matter, technology, human beings, and what sort of environment exists around the most magnetic objects known in the universe? Let's try a thought experiment. Not because astronomers expect it to happen. Quite the opposite. The scenario we're about to explore is extraordinarily unlikely, fortunately. But sometimes the best way to understand an object is to imagine what life would be like if it weren't safely tucked away thousands of light years from home. So imagine that one morning astronomers announce something surprising. They've discovered a magnetar much closer than anyone expected. Not next door. Not lurking somewhere beyond the moon. Nothing quite that alarming. But close enough that its presence becomes impossible to ignore. Close enough that scientists begin paying very careful attention. Close enough that humanity suddenly develops a new appreciation for distance. What would happen? What would it actually be like to live near one of the most magnetic objects in the universe? To answer that question, we first need to appreciate how strange magnetars really are. The problem is that human beings evolved in a remarkably gentle environment. Earth's gravity feels normal because we grew up with it. Earth's atmosphere feels normal because we've never known anything else. Earth's magnetic field feels normal because it quietly protects us without demanding attention. Nature on our planet generally operates within ranges that biology can tolerate. Magnetars do not. A magnetar is what happens when the universe takes a perfectly reasonable physical phenomenon and increases it to absurd levels. Imagine someone telling you they own a fast car. That sounds plausible. Then they explain that the car can travel around Earth several times every second. At that point, the word fast stops being useful. Magnetars create the same problem for magnetism. The word strong simply isn't enough. These objects possess magnetic fields that exceed ordinary experience by such enormous margins that comparison becomes difficult, and yet comparison is exactly what we'll attempt. Let's begin with something familiar, a refrigerator magnet. Simple, inexpensive, useful for attaching shopping lists to appliances. Its magnetic field is strong enough to hold paper in place, that's about it. Nobody worries about a refrigerator magnet accidentally destroying civilization. Now consider Earth's magnetic field. It stretches far into space. It helps shield us from charged particles arriving from the sun. It guides migrating birds. It allows compasses to function. Compared to a refrigerator magnet, it is much larger and more influential. Still manageable. Still familiar. Next come industrial magnets. Then MRI machines. Then laboratory magnets used by physicists. Each step upward reveals stronger and stronger fields. At every stage, the effects become more noticeable. Metal objects respond more dramatically. Safety precautions become more important. Engineering challenges become greater. Then we arrive at magnetars, and suddenly the entire ladder collapses. The difference between a magnetar and an MRI machine is so vast that they barely belong in the same conversation. It's a bit like comparing a candle to a star. Technically, both produce light. Practically speaking, they exist in completely different worlds. Suppose, purely hypothetically, that a magnetar approached close enough for its magnetic influence to become significant. The first casualties would likely be electronics. Modern civilization depends on electronics for nearly everything. Communication, navigation, banking, transportation, entertainment. The list goes on. Electronic systems function because charged particles move in carefully controlled ways. Magnetic fields influence charged particles. Very powerful magnetic fields influence them dramatically. Long before a magnetar posed any direct threat to people, it would begin causing trouble for technology. Computers might malfunction. Communication systems could experience interference. Satellites would become increasingly vulnerable. Engineers would suddenly find themselves facing challenges unlike anything encountered before. Fortunately, known magnetars remain extremely distant. This remains firmly within the realm of imagination. Still, the exercise reveals an important truth. Magnetars don't merely affect their immediate surroundings. Their influence extends outward through space. And because magnetic fields interact with matter in fundamental ways, that influence can become remarkably far-reaching. Let's move a little closer, again, not realistically close. Just close enough to continue the thought experiment. At sufficiently short distances, magnetic forces begin affecting matter itself. This is where things become particularly strange. Atoms are not solid little balls. They consist of charged particles arranged according to the rules of quantum physics. Electrons occupy specific regions around atomic nuclei. Chemical behavior depends on these arrangements. Magnetic fields influence charged particles. Extremely powerful magnetic fields influence them strongly. A magnetar's field can become so intense that atoms themselves begin behaving differently. The shapes of electron orbitals can change. Chemical properties can be altered. Matter no longer behaves exactly as it does under ordinary conditions. Pause for a moment and think about that. We are no longer discussing weather, or geology, or even gravity. We're discussing an environment capable of modifying atomic behavior. The magnetar is not merely stronger than familiar objects. It exists in a regime where the ordinary rules governing everyday matter begin to shift. This is one reason physicists find magnetars so fascinating. They provide natural laboratories for studying conditions impossible to create on Earth. No laboratory magnet can approach these strengths. No engineering project can replicate them. The universe performs the experiment for us. Astronomers simply observe. As remarkable as that sounds, things become stranger still. Consider light. Most of us think of light as something straightforward. It travels, it reflects, it illuminates objects. Simple enough. Yet in the presence of extraordinarily powerful magnetic fields, even light can behave in unexpected ways. According to quantum electrodynamics, the vacuum of space is not entirely empty. Under extreme conditions, magnetic fields can influence how light moves through that vacuum. Researchers have searched for evidence of these effects around magnetars, and observations increasingly suggest they may be real. Think about the implications. A magnetic field so powerful that it influences the behavior of light itself. Not because the light passes through matter, because the magnetic field alters the environment through which the light travels. This is one of those moments where astronomy begins sounding suspiciously like science fiction. Except the observations are real, the equations are real, the objects are real. Nature occasionally proves more imaginative than fiction writers. Now let's address a question people often ask. What would happen to a human near a magnetar? The honest answer is that the outcome would depend heavily on distance, very heavily. At safe astronomical distances, nothing unusual occurs, which is fortunate because that's where we currently reside. At dangerous distances, however, life becomes increasingly complicated. Strong magnetic fields can affect biological systems. Radiation becomes a concern. Charged particles become a concern. Various unpleasant consequences emerge. The details vary depending on exactly how close one imagines approaching. But generally speaking, magnetars are not ideal vacation destinations. The tourism industry there faces certain challenges. No beaches, no restaurants, no breathable atmosphere, and magnetic fields capable of causing significant trouble. Most travel brochures wisely omit them. Yet despite these dangers, magnetars remain incredibly important to science. Because by studying them, researchers learn about physics under conditions unavailable elsewhere. One particularly interesting aspect involves the region surrounding the star itself. We often imagine stars as isolated objects, a glowing sphere surrounded by empty space. Reality is usually more complicated. Magnetars possess magnetospheres. These are regions where the magnetic field dominates the behavior of charged particles. Earth has a magnetosphere. The Sun has one. Magnetars possess extraordinarily powerful versions. Within these regions, particles become trapped and accelerated. Radiation is generated. Energy moves through complex pathways. The magnetosphere becomes an active environment rather than empty space. In many ways, some of the most interesting magnetar physics occurs not inside the star but in the space surrounding it. This realization helped astronomers explain many observed bursts. Originally, researchers focused primarily on the crust, and rightly so. Starquakes clearly play an important role. But later studies suggested that magnetic rearrangements in the magnetosphere may also contribute. Imagine twisting a rubber band. Eventually it snaps into a different configuration. Energy is released. Magnetic field lines can undergo analogous processes. The resulting energy release contributes to the bursts observed by astronomers. In this picture, the magnetar becomes something like a gigantic magnetic engine. Stress accumulates. Fields twist. Energy builds. Eventually the system reorganizes. A burst erupts. Then the cycle begins again. One of the most fascinating aspects of this process is its persistence. Remember, these are dead stars. Fusion ended long ago. The original stellar life is over, and yet magnetars remain active for thousands or tens of thousands of years. their magnetic fields continue evolving, their crusts continue experiencing stress, their magnetospheres continue generating activity. The story doesn't end with the supernova. The supernova is merely the beginning. That idea fundamentally changed how astronomers think about stellar remnants. For a long time, dead stars were viewed primarily as leftovers. Interesting leftovers, certainly, but leftovers nonetheless. Magnetars demonstrated that stellar remnants could possess rich and dynamic lives of their own. Lives driven not by fusion, but by magnetism. Lives capable of producing phenomena visible across the galaxy. Lives capable of occasionally affecting Earth despite distances measured in tens of thousands of light years. And all of this emerged from objects no larger than cities. There is something wonderfully counterintuitive about that. The largest stars in the universe can be hundreds or even thousands of times larger than the Sun. Yet some of the most dramatic behavior occurs after collapse, after compression, after death. The giant becomes small. The small object becomes extraordinary. The universe seems rather fond of such reversals. By now, scientists had developed a reasonably complete picture of magnetars. They understood the role of magnetic fields. They understood starquakes. They understood giant flares. They understood why soft gamma repeaters repeatedly erupted, at least broadly. Across human history, repetition usually implies a pattern. The sun rises every morning, the seasons return each year, ocean tides advance and retreat. When something happens once, we call it an event. When it happens repeatedly, we begin looking for a reason. That instinct guided astronomers as they studied soft gamma repeaters. The first bursts were surprising enough. A dead star producing an enormous flash of gamma radiation was already an unusual discovery. But the real mystery wasn't the first explosion. It was the second, and the third, and the 10th, and the 100th. Again and again, these compact stellar remnants continued producing bursts. Some were tiny, some were substantial. A few were so powerful they became famous throughout the astronomical community. Yet regardless of size, they all pointed toward the same question. Why do these explosions keep happening? After all, most cosmic catastrophes are one-time events. A star explodes as a supernova. The event occurs, the star changes forever. The explosion doesn't repeat next Tuesday. A pair of neutron stars collide. The collision happens once. The stars merge. The story ends. Much of astronomy is built around singular events. Soft gamma repeaters refused to follow that rule. They behaved less like catastrophes and more like systems. Something was driving them. Something was storing energy. Something was repeatedly releasing that energy over time. The challenge was identifying exactly what that something might be. When astronomers first encountered repeating bursts, several possibilities were considered. Perhaps material was falling onto the neutron star. Perhaps the star's rotation played a role. Perhaps an unknown process was at work. Scientists explored each option carefully. That is one of the strengths of science. Researchers rarely fall in love with a single explanation immediately. They compare ideas, test assumptions, look for contradictions, allow observations to decide. Over time, the evidence increasingly pointed toward magnetars. And once magnetars entered the picture, the mystery began to unravel. The key insight involved energy storage. Every repeating process requires some kind of reservoir. A flashlight needs batteries. A car needs fuel. A hydroelectric dam stores energy in elevated water. Without a reservoir, repetition becomes impossible. The burst from soft gamma repeaters clearly required enormous amounts of energy. The source had to be storing that energy somewhere. And remarkably, the storage mechanism turned out to be magnetism itself. This remains one of the most fascinating aspects of magnetars. Their magnetic fields are not merely strong, they are energy reservoirs of astonishing scale. Imagine stretching a spring. The farther you stretch it, the more energy becomes stored. Release the spring and that energy emerges. Now imagine a spring the size of a city. Then imagine that spring contains more energy than entire civilizations could ever hope to produce. The analogy isn't perfect. Magnetic fields are not springs, but it captures the essential idea. Energy becomes stored. Energy remains trapped. Eventually energy gets released. That release appears to power the bursts. Of course, this explanation immediately raises another question. If magnetic fields store so much energy, why don't magnetars simply release everything at once? Why produce hundreds of smaller eruptions instead of one giant event? The answer lies in the way stress develops. Earth provides a useful comparison. Our planet contains enormous amounts of internal energy, yet that energy doesn't emerge in a single catastrophic release. Instead, stress accumulates gradually. Tectonic plates move, pressure builds, fault lines lock together. Eventually a region reaches its breaking point, an earthquake occurs, then stress begins accumulating again. The process repeats. Magnetars seem to operate according to a broadly similar principle. Their magnetic fields evolve continuously. The changes are slow, sometimes very slow. Years may pass with little obvious activity. But beneath the surface, stress continues building. The magnetic field twists. Field lines shift. Forces act upon the crust. The star resists, at least for a while. Then something gives way. A fracture occurs. A rearrangement takes place. Stored magnetic energy is suddenly released. A burst appears. The magnetar survives. The cycle starts over. This framework elegantly explains why explosions continue occurring long after the star itself has died. The source of the energy isn't stellar fusion. Fusion ended thousands of years earlier. Instead, the source is the gradual evolution of the magnetic field. As long as magnetic stresses continue developing, future bursts remain possible. In a sense, magnetars spend much of their existence winding themselves up. Then, periodically, they unwind. One particularly interesting feature of soft gamma repeaters is that the bursts often arrive in clusters. Astronomers refer to these periods as active episodes. For months or even years, a magnetar may remain relatively quiet. Then suddenly dozens of bursts appear over a short period. Afterward, activity decreases once again. The pattern resembles seismic activity on Earth. A major earthquake is often followed by aftershocks. Stress redistributes. Additional adjustments occur. The system gradually settles into a new configuration. Something similar may happen within magnetars. A significant magnetic rearrangement could trigger a series of related events. One burst alters conditions inside the star. That alteration creates new stresses. Additional bursts follow. The magnetar experiences a storm of activity before eventually calming down. Observations strongly support this idea. Many soft gamma repeaters spend long intervals appearing inactive. Then they enter remarkably energetic phases. The timing isn't perfectly predictable. The exact details vary, but the overall pattern appears again and again. Another fascinating aspect involves magnetic field decay. Unlike Earth's magnetic field, which changes relatively slowly, magnetar fields gradually weaken over time. The process is complex. Magnetic energy doesn't simply vanish. Instead, it gets converted into other forms: heat, radiation, particle acceleration. Various physical processes contribute. As the magnetic field evolves and decays, additional energy becomes available. This helps explain why magnetars remain active long after their formation. The magnetic field itself acts as a long-term power source. Imagine charging an enormous battery, not one capable of running a phone, not one capable of running a city, a battery capable of powering extraordinary cosmic events for thousands of years. That comparison isn't entirely accurate. Magnetic fields aren't batteries. But again, the basic idea works. Energy becomes stored. Energy leaks away gradually. Occasionally, large amounts emerge suddenly. The bursts are one consequence of that process. Scientists have also discovered that magnetars produce activity even when dramatic bursts aren't occurring. X-ray observations reveal that many remain surprisingly bright. This brightness appears linked to magnetic heating. The magnetic field doesn't merely generate occasional explosions. It continuously influences the star's behavior. Energy moves through the crust. Temperatures remain elevated. Radiation escapes into space. The magnetar remains active in subtle ways even during quiet periods. This realization changed how astronomers viewed these objects. Early studies focused heavily on bursts because bursts were obvious. They captured tension, they generated headlines, they produced dramatic data. Later observations revealed a more nuanced picture. The explosions are important, but they represent only one aspect of magnetar life. Even between eruptions, magnetic processes continue shaping the star. The object remains dynamic, active, evolving. The explosions are simply the most visible symptoms. Imagine a volcano. Visitors often focus on eruptions, the explosions, the lava, the ash. Yet volcanic systems remain active even between eruptions. Magma moves underground. Pressure changes. Heat flows. Important processes continue long before the next dramatic event. Magnetars appear similar. The bursts attract attention. The underlying evolution never truly stops. Researchers have identified several categories of magnetar activity. Short bursts represent the most common. These events typically last fractions of a second. The energy release is substantial but relatively modest by magnetar standards. Then come intermediate flares, longer, more energetic, less common. Finally, there are giant flares. The rare giants that briefly transform magnetar into one of the brightest high-energy sources in the galaxy. Remarkably, all of these phenomena may arise from the same underlying physics. Different amounts of stored energy. Different scales of magnetic rearrangement. Different degrees of crustal failure. The mechanism remains broadly similar. The outcome varies. This is another reason the magnetar model proves so successful. A single framework explains many observations. Scientists generally appreciate explanations that solve multiple puzzles simultaneously. Nature often rewards simplicity, not always, but often. The magnetar model managed to account for repetition, energy output, burst statistics, giant flares, and long-term evolution. That's an impressive achievement. Still, there remain unanswered questions. Researchers continue debating exactly how magnetic fields evolve within neutron stars. The internal structure remains partly uncertain. The behavior of matter at such extreme densities remains difficult to calculate. Some details remain mysterious. That is perfectly normal. Scientific understanding rarely arrives fully completed. Instead, it improves gradually, piece by piece. Observation by observation. What matters is that the overall picture now makes sense. The explosions keep happening because the magnetic field keeps changing. Stress keeps accumulating. Energy keeps being stored. The magnetar continues evolving long after its birth. As long as those processes continue, future bursts remain possible. Eventually, however, the activity declines. Magnetic fields weaken. Energy reserves diminish. The object becomes quieter. A magnetar does not remain extraordinarily active forever. Even cosmic monsters age. Even the most powerful magnetic fields eventually lose strength. Over hundreds of thousands of years, the dramatic bursting behavior gradually fades. The magnetar settles into a calmer existence. Yet during its active lifetime, it remains one of the most fascinating objects in the galaxy. A dead star powered by magnetism. An object capable of shaking Earth's atmosphere from across the Milky Way. A stellar remnant that refuses to stay silent. Some discoveries begin with a flash. Others begin with a pattern. Astronomers are particularly fond of patterns because the universe tends to hide its secrets inside them. A single event can be exciting. Two similar events can be interesting, but when the same subtle feature appears again and again, researchers start paying very close attention. That's exactly what happened with soft gamma repeaters. For years, scientists focused primarily on the obvious parts of the bursts, the tremendous energy, the sudden flashes, the giant flares capable of affecting Earth's atmosphere from tens of thousands of light years away. Those features naturally attracted attention. They were dramatic, they were unusual, they were impossible to ignore. Yet buried beneath all that excitement was something quieter, something smaller, something hidden inside the bursts themselves. At first glance, these signals seemed insignificant, tiny fluctuations, minor variations. Subtle changes in brightness occurring over fractions of a second, the kind of details that might easily disappear beneath the larger story. But astronomy has a long history of rewarding patience, and when researchers began examining these fluctuations carefully, they discovered something remarkable. The bursts weren't merely releasing energy, they were carrying information. In a sense, magnetars were talking, not with words, of course, not with messages, not with anything resembling language, but through patterns, through vibrations, through oscillations hidden inside the radiation. And by learning how to interpret those signals, astronomers gained an entirely new way of studying some of the most extreme objects in existence. The story begins with giant flares. Ordinary soft gamma repeater bursts are useful. They reveal valuable information, but giant flares are special. They release enormous amounts of energy. They remain detectable for longer periods. And because they are so bright, scientists can examine their details with greater precision. The most famous examples occurred in 1979, 1998, and 2004. Each event provided an opportunity. A brief moment during which one of the galaxy's most powerful magnetic objects revealed itself in extraordinary detail. When researchers analysed the data from these giant flares, they noticed something unusual. The radiation wasn't perfectly smooth. Instead, it contained faint rhythmic variations, tiny pulses, subtle oscillations, patterns repeating at specific frequencies. Initially, scientists weren't entirely sure what they were seeing. Whenever unexpected signals appear in astronomical data, caution is essential. Instruments can introduce artifacts, computers can generate false patterns. Random noise can occasionally create misleading results. Extraordinary claims require careful verification, so researchers checked, then checked again, then checked again. The oscillations persisted. Different instruments detected them. Independent analyses confirmed them. The signals appeared to be real, and if they were real, they raised a fascinating question. What was producing them? One possibility quickly emerged. The magnetar itself might be vibrating. To understand why this idea generated so much excitement, imagine a bell. Strike a bell with a hammer and it rings. The sound carries information about the bell's size, shape, composition, and structure. A large bell sounds different from a small one. A thick bell sounds different from a thin one. The vibrations reveal characteristics of the object producing them. Scientists realized that giant flares might be doing something similar. A massive starquake releases tremendous energy. The crust cracks. Magnetic fields reorganize. The entire neutron star may begin vibrating. Those vibrations could then influence the radiation escaping into space. If that interpretation was correct, astronomers were effectively listening to the ringing of a dead star. The idea sounded extraordinary. It still does. Yet evidence continued supporting it. Researchers identified multiple frequencies within the bursts. Some oscillations occurred dozens of times per second. Others appeared hundreds of times per second. Each frequency potentially corresponded to a particular vibration mode within the neutron star. Just as a musical instrument can vibrate in multiple ways simultaneously, a magnetar may support numerous oscillation patterns, and each pattern contains clues. The comparison with musical instruments turns out to be surprisingly useful. Consider a guitar string. When plucked, it vibrates at a fundamental frequency. Additional harmonics appear as well. The resulting sound depends on the properties of the string, its length, its tension, its mass. Change those properties and the sound changes too. Magnetars appear to behave similarly, albeit on a scale that is considerably more dramatic. The frequencies observed during giant flares depend on the star's structure, its density, its magnetic field, its crust, its interior. Measure the frequencies and you learn something about the object itself. Astronomers sometimes refer to this approach as neutron star seismology. The name is borrowed from Earth science. Geologists use earthquakes to study Earth's interior. Astronomers use starquakes to study neutron stars. The principle is remarkably similar. When an earthquake occurs, seismic waves travel through our planet. Scientists measure those waves. The measurements reveal information about Earth's internal layers, the crust, the mantle, the core. Without ever drilling thousands of kilometers into the planet, researchers can infer what lies beneath the surface. Magnetars offer a cosmic version of the same technique. A giant flare produces vibrations. Those vibrations affect the emitted radiation. Scientists measure the oscillations. The oscillations reveal information about the star's interior. It's an elegant solution to a difficult problem. After all, neutron stars are not exactly easy to inspect directly. They're tiny, distant, incredibly dense, and surrounded by extreme environments. Nobody is sending a probe anytime soon. Listening to vibrations becomes one of the few available options. One of the most important discoveries involved what are known as quasi-periodic oscillations. The name is admittedly less exciting than the phenomenon itself. Astronomers often prioritize precision over drama when naming things. A quasi-periodic oscillation is a pattern that repeats approximately, though not perfectly. Think of a drummer keeping a rhythm while occasionally varying the beat slightly. The overall pattern remains recognizable. Small deviations occur. Researchers identified such oscillations in several giant flares. The frequencies appeared too structured to be random. Something physical was generating them, and the leading explanation pointed toward vibrations within the magnetar. This opened an entirely new window into neutron star physics. For decades, many aspects of neutron star interiors remained deeply uncertain. Scientists possessed theoretical models. They possessed mathematical calculations. They possessed computer simulations. But direct observational evidence was limited. The oscillations changed that. Suddenly there was a way to test ideas. Different models predicted different vibration frequencies. Observations could distinguish between them. Some theories survived. Others required modification. The process moved understanding forward. Another intriguing aspect involves the role of magnetic fields. Remember, magnetars are not ordinary neutron stars. Their magnetic fields are extraordinary. So extraordinary, in fact, that the fields themselves influence the vibrations. Imagine trying to study the sound of a bell while giant invisible forces continuously pull on it from every direction. The situation becomes complicated very quickly. Magnetar oscillations are shaped not only by the crust and interior matter, but also by the magnetic field. The field acts almost like an additional structural component. It participates in the dynamics. It alters the frequencies. It changes the behavior of the vibrations. This makes interpretation challenging, but it also makes the signals even more valuable, because if the magnetic field affects the oscillations, then the oscillations contain information about the magnetic field itself. Scientists gain insight into two mysteries simultaneously: the interior structure and the magnetic environment. It's rather efficient. The universe occasionally provides data packages with multiple benefits. Interestingly, some researchers suspect that the vibrations may not be confined solely to the crust. The interior of a neutron star remains one of the most mysterious environments known. Matter there exists under pressures and densities impossible to reproduce in laboratories. Physicists continue debating exactly what forms that matter might take. Some models suggest exotic states. Others propose unusual particle interactions. The details remain uncertain. If vibrations extend into these deeper regions, they may carry information from environments that would otherwise remain forever hidden. Imagine hearing echoes from a room you can never enter. The echoes might still reveal its size, its shape, its contents. The oscillations detected from magnetars may function in a similar way, tiny clues emerging from one of the most inaccessible places in the universe. Not every burst contains these signals. That is another reason giant flares are so important. Their tremendous brightness allows researchers to detect subtle features that would otherwise be lost. The stronger the flare, the easier it becomes to identify delicate oscillation patterns. Unfortunately, giant flares are rare, very rare. Astronomers cannot simply schedule one whenever convenient. The universe remains stubbornly unwilling to follow observation calendars. Researchers must wait, sometimes for years, sometimes longer. Patience remains one of astronomy's most important skills. Still, every new event adds to the growing collection of data. Every observation improves statistical confidence. Every giant flare offers another opportunity to refine models. The field continues advancing, and the implications extend beyond magnetars themselves. Understanding neutron stars matters for many branches of astrophysics. These objects represent natural laboratories for extreme gravity, extreme density, extreme magnetism. Lessons learned from magnetars often influence broader theories. A better understanding of neutron stars improves our understanding of stellar evolution. Nuclear physics, high-energy astrophysics, even gravitational wave astronomy. The connections spread outward in fascinating ways. What began as a mysterious repeating burst becomes a tool for exploring some of the deepest questions in modern science. There's something wonderfully ironic about the process. The bursts that once confused astronomers now help educate them. The signals that initially seemed like noise now provide valuable information. The explosions themselves have become sources of insight. Rather than obscuring the star, the bursts reveal it. They act like flashes of illumination, brief moments during which hidden properties become visible, or perhaps audible is the better word. Because in many respects, astronomers have learned to listen rather than merely observe. They listen to oscillations, they listen to frequencies, they listen to patterns hidden within the radiation. And through that listening, they uncover details about objects located thousands of light years away. Yet as impressive as these discoveries are, another mystery continued attracting attention. Magnetars were already explaining soft gamma repeaters remarkably well. Their magnetic fields explain the energy. Starquakes explained the bursts. Oscillations revealed their internal structure. The picture seemed increasingly complete. Then astronomers noticed something else occurring elsewhere in the universe. Brief radio flashes, extraordinarily powerful, unexpected, and strangely familiar. These events became known as fast radio bursts. For years, their origin remained one of astronomy's greatest puzzles. Eventually, some researchers began wondering whether the answer might involve a familiar suspect. A suspect with a history of surprising behavior. A suspect capable of releasing enormous amounts of energy. A suspect already known for producing mysterious bursts. The question was simple. Could magnetars be responsible for other cosmic mysteries as well? For much of scientific history, solving one mystery usually led directly to another. Astronomers identify a strange object. They study it. They develop a theory. The theory works. Everyone celebrates briefly. Then someone notices a new phenomenon that doesn't fit, and the entire process begins again. Magnetars followed exactly this pattern. At first, they were the mystery. Researchers spent decades trying to understand why certain dead stars produced repeated bursts of gamma radiation. Eventually, the pieces fell into place. The enormous magnetic fields explained the energy. Starquakes explained the bursts. Giant flares explained the most dramatic events. The overall picture became increasingly convincing. For many scientists, the case seemed largely solved. Not every detail, certainly. Science rarely reaches a final endpoint. But the central mystery appeared under control. Then the universe introduced another puzzle. A completely different puzzle, or so it seemed at first. The story began in 2007. Astronomers examining archival radio telescope data noticed something unusual. A brief flash of radio waves had appeared. The signal lasted only a few milliseconds, then it vanished. The event was powerful, extremely powerful, powerful enough that it immediately attracted attention. The source became known as the Lorimer Burst, named after astronomer Duncan Lorimer, whose student discovered it while analysing observations. At first, nobody knew what to make of it. One burst isn't enough to establish a new category of object. Data errors happen, interference happens, unexpected instrumental effects happen. Scientists remained cautious. Then additional events appeared, and then more. Gradually a pattern emerged. The universe was producing brief flashes of radio energy, incredibly bright flashes, incredibly short flashes, events lasting mere thousandths of a second. These phenomena eventually became known as fast radio bursts, or FRBs. The name was practical, straightforward, very astronomer-like: fast, radio, burst, simple. Yet behind that simple name lurked one of the biggest mysteries in modern astronomy. What was producing them? The observations immediately raised difficult questions. The bursts were extraordinarily bright. The bursts were extraordinarily brief. And many appeared to originate from astonishing distances. Some came from galaxies billions of light-years away. That meant the sources had to be incredibly powerful. A signal crossing billions of light-years and still reaching Earth with measurable strength requires an extraordinary origin. Researchers proposed dozens of explanations. Perhaps neutron stars were involved. Perhaps black holes played a role. Perhaps exotic cosmic phenomena remained undiscovered. Some theories became extremely creative. Others bordered on speculative science fiction. A few involved alien civilizations. Whenever astronomy encounters something mysterious, someone eventually mentions aliens. It's practically a tradition at this point. Yet most scientists suspected a natural explanation. The challenge was identifying which one. For years, fast radio bursts remained frustratingly elusive. Part of the difficulty involved their brevity. Imagine trying to study lightning using a camera that takes one photograph every few hours. You might occasionally capture a strike. Most of the time, you would miss it entirely. Early FRB research faced similar challenges. The bursts appeared suddenly, lasted milliseconds, then disappeared. Tracking them was difficult. Understanding them was even harder. The situation became more interesting when astronomers discovered repeating fast radio bursts. This development immediately changed the conversation. Originally, many theories assumed FRBs resulted from catastrophic events. A star explodes. A merger occurs. Something destroys itself. The burst appears. The story ends. That explanation worked reasonably well for one-time events. Repeating bursts created a problem. If the source repeated, then the source survived. And if the source survived, the explanation had to account for continued activity. At this point, some researchers began noticing a familiar pattern. A compact object, enormous energy releases, repeated bursts, long periods of apparent inactivity followed by renewed activity. The similarities were difficult to ignore. Magnetars suddenly looked very interesting. After all, they already possessed many necessary ingredients. They were capable of releasing extraordinary amounts of energy. They were known to produce bursts. They could survive those bursts. And they were among the most extreme objects in the universe. If any known object seemed capable of generating mysterious flashes, magnetars ranked high on the candidate list. The idea gained traction. Researchers developed models. Computer simulations explored possible mechanisms, observational evidence accumulated, yet definitive proof remained elusive. Astronomy often proceeds this way. Theories emerge before confirmation arrives. Scientists build cases gradually, clue by clue, observation by observation. Then, in 2020, something remarkable happened. For the first time, astronomers observed a fast radio burst originating from within our own galaxy. This was important. Very important. Most known FRBs came from immense distances. Studying nearby examples offered significant advantages. Researchers could gather better data. More instruments could participate. The source could be examined in greater detail. The object responsible turned out to be a magnetar, specifically a magnetar known as SGR 1935+2154. The name itself was enough to attract attention. The first three letters mattered. SGR, soft gamma repeater, the very phenomenon we've been discussing. Suddenly two previously separate mysteries appeared connected. During an active period, SGR 1935+2154 produced a powerful radio burst remarkably similar to extragalactic fast radio bursts. The event electrified the astronomical community. For years, magnetars had been considered possible explanations. Now direct evidence existed linking at least some FRBs to magnetar activity. The discovery did not solve every aspect of the puzzle. Far from it. But it represented a major breakthrough. Imagine spending years trying to identify an unknown animal based only on distant footprints. Then one day the animal walks directly in front of a camera. That's roughly how the discovery felt. The connection wasn't merely theoretical anymore, it was observational, real, measurable, and incredibly exciting. The implications extended beyond fast radio bursts. If magnetars could produce FRBs, perhaps they contributed to other mysterious phenomena as well. After all, magnetars possess a remarkable combination of properties: extreme magnetic fields, extreme densities, extreme energies. Whenever astronomers encounter unusual observations, objects with extreme properties naturally attract attention. One area of ongoing research involves ultra-high energy cosmic rays. These particles travel through space at extraordinary speeds. Some possess energies millions of times greater than those achieved in human particle accelerators. Their origins remain partially mysterious. Researchers continue investigating potential sources. Magnetars occasionally appear in those discussions. Theoretical models suggest they may contribute under certain conditions. The case remains unresolved. But the possibility remains intriguing. Another area involves gravitational waves. Neutron stars have already proven important in gravitational wave astronomy. Collisions between neutron stars generate detectable ripples in space-time. Magnetars may eventually contribute additional surprises. Large star quakes could potentially produce subtle gravitational wave signals. Current detectors are not yet sensitive enough to observe most such events. Future instruments may change that. If they do, astronomers could gain entirely new ways of studying magnetars. Imagine not merely observing their radiation, but detecting distortions in space-time generated by their activity. The prospect is exciting. The technology continues improving. The future remains open. Then there are gamma-ray mysteries. High-energy astrophysics contains no shortage of unanswered questions. The universe produces radiation across enormous energy ranges. Researchers constantly search for explanations. Magnetars occasionally emerge as candidates. Sometimes they fit, sometimes they don't. Either way, their extreme nature makes them difficult to ignore. One reason magnetars continue appearing in these discussions is their versatility. Many astronomical objects excel at one thing. Black holes dominate gravity. Pulsars provide extraordinary timing precision. White dwarfs illustrate stellar evolution. Magnetars influence numerous areas simultaneously. Their magnetic fields affect particle acceleration. Their bursts generate radiation. Their interiors reveal exotic physics. Their flares influence surrounding environments. They are astrophysical multitaskers. The more researchers study them, the more connections appear. This pattern has repeated throughout scientific history. Certain discoveries begin narrowly. Over time, their importance expands. Electricity once seemed like a curiosity. DNA once seemed like a biochemical detail. Magnetars may represent something similar within astrophysics. Originally they explained soft gamma repeaters. Now they influence discussions involving fast radio bursts, neutron star physics, particle acceleration, high-energy radiation, and potentially much more. Each year brings additional insights. Each new observation reveals another layer, yet uncertainty remains, and that's perfectly normal. Science advances through uncertainty. Questions drive progress. Mysteries create opportunities. The fact that magnetars continue appearing in unresolved discussions is not a weakness. It's evidence that researchers are exploring actively, testing ideas, expanding understanding. One particularly fascinating aspect involves the possibility that different magnetars behave differently. Not every magnetar appears equally active. Not every burst looks identical. Not every flare follows the same pattern. This diversity suggests a complex population. Age matters. Magnetic field strength matters. Environment matters. History matters. The details remain subjects of ongoing investigation. It's possible that some magnetars produce fast radio bursts frequently while others rarely do. It's possible that some contribute to cosmic ray populations while others do not. Nature rarely treats every object identically. The universe generally prefers variety. As observations improve, astronomers continue discovering that variety. More magnetars, more bursts, more connections, more questions. And perhaps that is the most interesting part of all. The story keeps growing. A few decades ago, soft gamma repeaters represented a small mystery involving strange bursts from dead stars. Today, magnetars sit near the center of multiple active research fields. Their influence extends far beyond their original discovery. They have become key players in modern astrophysics. Yet despite all these extraordinary behaviors, a broader question remains. What do magnetars actually teach us about stellar death itself? Throughout most of this story, we focused on activity, bursts, flares, magnetic storms, starquakes, explosions powerful enough to be detected across the galaxy. That's understandable. After all, these events are what first attracted astronomers to soft gamma repeaters in the first place. A quiet object rarely makes headlines. An object capable of releasing more energy in a fraction of a second than the sun produces in hundreds of thousands of years tends to receive rather more attention. Yet there is another perspective worth considering. Not every magnetar is bursting right now. Not every magnetar is experiencing a giant flare. Not every magnetar is shaking itself apart with starquakes. Most of the time, even the most active magnetars spend their lives doing something far less dramatic. They age, and like everything else in the universe, aging changes them. This raises an intriguing question. What happens when a magnetar finally grows quiet? The answer turns out to reveal something important not only about magnetars, but about stellar death itself. For centuries, people imagined death in astronomy as a fairly simple process. A star shines, the star dies. The star fades away. End of story. That picture isn't entirely wrong. It just isn't complete. The universe is rarely satisfied with simple endings. Massive stars may explode as supernovae. Neutron stars may remain behind. Some neutron stars become magnetars. Magnetars produce bursts. The bursts continue for thousands of years, and eventually even that activity begins to fade. But the fading process is far more interesting than one might expect. To understand why, let's return briefly to the source of the magnetar's power. Unlike ordinary stars, magnetars are not fueled by fusion. Hydrogen is no longer being converted into helium. The vast nuclear furnace that once powered the parent star disappeared long ago. Instead, magnetars are powered primarily by magnetic energy. The magnetic field acts as an enormous reservoir. As long as that reservoir exists, activity remains possible. Starquakes can occur. Magnetic reconnection events can occur. Bursts can occur. The key phrase is as long as. Nothing lasts forever. Not stars, not galaxies, not magnetic fields. Over time, the magnetar's magnetic field gradually weakens. This process is known as magnetic field decay. The name sounds simple. The reality is rather more complicated. The field does not simply switch off. It evolves. It changes. It transfers energy into other forms. Heat, radiation, particle acceleration. Various physical mechanisms slowly drain the enormous magnetic reservoir. The process takes thousands to hundreds of thousands of years. From a human perspective, that's an extraordinarily long time. From a cosmic perspective, it is surprisingly brief. A star may live for millions or billions of years. A magnetar's most active phase occupies only a tiny fraction of that lifespan. In a sense, magnetars burn through their magnetic energy, much like massive stars burn through nuclear fuel. Fast, intense, spectacular, then gradually quieter. This comparison is one of the fascinating ironies of astrophysics. The stars that become magnetars are often among the most massive stars in existence. Massive stars already live relatively short lives. Then their remnants continue the trend by living unusually energetic afterlives. Neither stage is particularly calm. Nature seems to have given them a preference for drama. As magnetic field decay progresses, several things happen. The bursts become less frequent. The starquakes become less energetic. The overall activity level declines. The magnetar begins transitioning into something more ordinary. Not ordinary by everyday standards, of course. A neutron star never becomes truly ordinary. But ordinary relative to other neutron stars. The object slowly loses the characteristics that once made it exceptional. Imagine a volcano. During its most active periods, eruptions occur frequently. Lava flows. Ash clouds rise into the sky. The volcano dominates the landscape. Then activity decreases. Small eruptions replace large ones. Long quiet intervals appear. Eventually the volcano may become dormant. The mountain remains, its history remains, its structure remains. But the dramatic activity fades. Magnetars seem to follow a broadly similar path. The object survives, the bursts diminish, the monster gradually settles down. Astronomers believe many neutron stars observed today may actually be elderly magnetars, objects that once possessed astonishing magnetic fields but have since grown quieter. The evidence supporting this idea continues to accumulate. Researchers have identified neutron stars whose current properties suggest they may be descendants of ancient magnetars. Their active youth is gone, only subtle clues remain. This realization leads to an interesting thought. How many magnetars has the Milky Way produced? The answer is almost certainly far larger than the number we currently observe. The reason is simple. We tend to notice active magnetars. Quiet ones are much harder to identify. Imagine trying to count volcanoes by looking only for eruptions. You would inevitably miss many dormant examples. Something similar may happen with magnetars. The active phase is relatively brief. The quiet phase may last much longer. As a result, numerous former magnetars could be scattered throughout the galaxy, largely unnoticed. The Milky Way itself contains hundreds of billions of stars. Among those stars are countless stellar remnants, white dwarfs, neutron stars, black holes. The exact number of neutron stars alone is staggering. Astronomers estimate that our galaxy may contain hundreds of millions of them. Most remain invisible to us. Many are too faint to detect easily. Some emit little radiation. Others simply haven't been found yet. The vast majority quietly occupy regions of space far beyond human awareness. This is worth pausing to appreciate. At this very moment, our galaxy may contain millions upon millions of dead stars. Not ancient stars that are about to die, not stars currently exploding, stars that have already completed their stellar lives. The Milky Way is, in many ways, a galaxy built from remnants. Every generation of stars leaves something behind, and among those remnants are objects that continue evolving long after their parent stars disappear. Magnetars represent one of the most dramatic examples. Their existence forces us to rethink what stellar death actually means. The phrase dead star creates a particular image, something inert, something finished, something no longer capable of meaningful activity. Yet magnetars challenge that image repeatedly. They continue generating radiation. They continue reshaping magnetic fields. They continue producing bursts. They continue influencing their surroundings. Death, in this context, is not the end of the story. It is merely the end of fusion. The object itself remains active. This distinction matters. Human language sometimes struggles with astrophysics because familiar words carry familiar assumptions. When we hear dead, we imagine stillness. Astronomers use the same word while describing objects capable of shaking Earth's atmosphere from 50,000 light-years away. Clearly, different definitions are involved. A dead star is not necessarily a quiet star. A dead star is simply a star that no longer generates energy through fusion. Everything else depends on the circumstances, and some circumstances produce remarkable outcomes. Consider the broader implications. For billions of years, stars have formed throughout the galaxy. Many lived peacefully, many died quietly, others exploded. A small fraction became neutron stars, an even smaller fraction became magnetars. Every one of those objects contributed to the evolving history of the Milky Way. The galaxy we inhabit today is partly shaped by these processes. The heavy elements inside your body originated in earlier generations of stars. Supernovae scattered those elements into space. New stars formed, new planets formed. Eventually life emerged. The chain stretches backward across cosmic time. Magnetars occupy one branch of that enormous story. A rare branch, an extreme branch, but an important one. Their magnetic fields influence surrounding environments. Their bursts inject energy into space. Their evolution provides insight into fundamental physics. They help astronomers understand how matter behaves under extraordinary conditions. And perhaps most importantly, they remind us that the universe is often more complicated than first impressions suggest. Something can be dead and active simultaneously. A star can end and continue. An explosion can mark a beginning rather than a conclusion. These ideas appear repeatedly throughout astronomy. Supernovae create new possibilities. Stellar remnants continue evolving. Galaxies recycle material into future generations of stars. The universe is remarkably good at transforming endings into transitions. Magnetars illustrate that principle beautifully. There is another reason scientists remain fascinated by them. Despite decades of research, many questions remain unanswered. Researchers continue debating details of magnetic field evolution. The exact structure of neutron star interiors remains uncertain. The relationship between magnetars and fast radio bursts remains an active area of investigation. Future observations will undoubtedly reveal surprises. They always do. Astronomy has a long tradition of replacing old mysteries with new ones. Every breakthrough creates additional questions. Every answer opens another door. Magnetars are unlikely to be an exception. The more we learn, the more interesting they become. And eventually even the most active magnetar reaches a stage where its great eruptions become rare, its magnetic field weakens. Its crust experiences less stress. The dramatic bursts that once defined its existence fade into memory. The object survives, older, quieter, less explosive, still extraordinary, but no longer the cosmic firebrand it once was. In some respects, the transition resembles a star entering retirement, a very unusual retirement, a retirement involving extreme gravity and exotic matter, but retirement nonetheless. The magnetar has spent thousands of years announcing itself across the galaxy. Eventually it grows calmer. The great magnetic reservoir empties. The universe moves on. Yet even after the bursts stop, the lessons remain. Because every active magnetar we observe today offers a glimpse into a temporary phase, a brief period in the life of an extraordinary object, a period that eventually ends. And when astronomers step back to look at the bigger picture, they find something remarkable. The galaxy is filled with stellar remnants at every stage of evolution, some newly formed, some highly active, some slowly fading, some perhaps entirely dormant. Together they create a vast population of objects whose stories continue long after their parent stars have vanished. And among all of them, soft gamma repeaters occupy a special place. They revealed that stellar death is not necessarily the end. They revealed that magnetic fields can power extraordinary phenomena. They revealed that some of the smallest objects in the universe can produce some of its largest surprises. Before we finish tonight's journey, I'd like to return to something we briefly touched upon at the very beginning, the idea of a dead star. It's a phrase astronomers use constantly, a convenient phrase, a useful phrase. And yet after everything we've explored together, it no longer feels quite as straightforward as it once did. When most people hear the word dead, they imagine stillness, silence, an ending, a completed story. That's a perfectly reasonable assumption. After all, death tends to imply finality in our everyday experience. The activity stops, the process concludes, the chapter closes. Yet throughout the universe, things are often a little more complicated than our language suggests. Stars provide one of the best examples. A massive star may spend millions of years shining. Hydrogen fuses into helium. Energy flows outward. Gravity presses inward. A delicate balance persists. Then eventually the fuel runs low. The balance fails. The star explodes. A supernova briefly outshines entire galaxies. From a distance, that seemed like a natural ending. The star lived. The star died. The story is over. But tonight we've discovered that for certain stars the story continues. Not in the way anyone expected. Not through fusion. Not through renewed youth. Not through some cosmic resurrection. Instead, the aftermath becomes its own extraordinary chapter. A neutron star remains. Compact remnant only a few kilometers across. A stellar core compressed to astonishing densities, an object carrying more mass than the Sun inside a sphere roughly the size of a city. Already that would be remarkable enough. Most astronomical objects would happily stop there. The universe, however, appears to have decided that neutron stars weren't quite strange enough. So some of them became magnetars, and magnetars changed everything. Over the course of this journey, we've encountered some astonishing numbers. Magnetic fields trillions of times stronger than Earth's. Starquakes capable of releasing more energy than countless earthquakes combined. Giant flares detectable across tens of thousands of light years. Bursts powerful enough to leave measurable fingerprints in Earth's atmosphere despite crossing vast stretches of interstellar space. At times, the scale has almost become difficult to process. That's one of the recurring challenges of astronomy. The universe rarely limits itself to comfortable numbers. Whenever we think we've reached an extreme, nature often reveals another, a larger star, a stronger magnetic field, a more energetic explosion, a stranger object. Magnetars sit comfortably within that tradition. They remind us that some of the most fascinating things in existence occur under conditions far removed from ordinary human experience. And yet, despite all their extremes, magnetars tell a surprisingly relatable story. Not because they resemble us, a city-sized sphere of neutron matter with a magnetic field capable of distorting atoms is not especially relatable. The connection lies elsewhere. It lies in persistence. One of the defining features of soft gamma repeaters is that they refuse to remain silent. Again and again they remind astronomers of their presence. Years may pass, decades may pass, then another burst arrives, another flare, another signal crossing the galaxy. The star is gone. The activity remains. That persistence is what made them so mysterious. It's also what made them so important. When astronomers first detected repeating bursts of gamma radiation, the observations didn't fit neatly into existing ideas. Dead stars weren't supposed to behave this way. At least not according to the models available at the time. The bursts challenged assumptions, and science advances whenever assumptions are challenged successfully. This is one of the themes that quietly appears throughout the history of astronomy. The universe repeatedly surprises us. Ancient observers thought stars were fixed points of light. Then they discovered stellar motion. Scientists once believed galaxies were the entire universe. Then they discovered countless others. Researchers thought gamma-ray bursts represented one category of phenomenon. Then soft gamma repeaters appeared and complicated matters. Each discovery adds detail. Each discovery expands the picture. Each discovery reminds us that reality is usually richer than our first explanation. Magnetars occupy a particularly interesting place within that tradition because they transformed an ending into a beginning. The supernova was not the final act, it was merely the transition. What followed became its own story. A story involving magnetic fields of unimaginable strength. A story involving starquakes and giant flares. A story involving bursts that repeated across decades. A story that continues today. Even now, somewhere within our galaxy, magnetars are quietly evolving. Magnetic fields are shifting. Stress is accumulating. Energy is being stored. Most of these objects are invisible to the unaided eye. Many remain unknown. Yet the processes continue regardless. The galaxy is busy in ways we rarely notice. This idea becomes even more fascinating when we widen our perspective. The Milky Way contains hundreds of billions of stars. Many have already completed their lives. Many will eventually do so. Across cosmic history, countless supernovae have occurred. Countless neutron stars have formed. A fraction became magnetars. Some are active now. Others have already grown quiet. Still others may be waiting to surprise astronomers in the future. The result is a galaxy filled with remnants. Not empty remnants. Not lifeless remnants. Remnants still participating in the ongoing story of the cosmos. When we look up at the night sky, we tend to focus on stars that shine. That's understandable. They're visible. They're beautiful. They're easy to notice. Yet hidden among them are stellar remnants. Objects whose brightest days are long behind them. Objects that nevertheless remain important. The universe, it turns out, has many ways of staying active. Sometimes activity comes from youth. Sometimes it comes from transformation. And sometimes it comes from energy stored long ago, gradually finding new ways to emerge. Magnetars embody that last category beautifully. They are ancient engines powered by reservoirs built during extraordinary events. Even after their original source of power disappears, the consequences continue. That realization leads naturally toward another thought. Throughout this journey, we've repeatedly encountered scales that dwarf human experience. Thousands of light years, millions of years, magnetic fields beyond imagination, explosions of staggering power. It's easy to feel small in comparison. Astronomy often has that effect. Yet, there's another way to view the situation. The fact that human beings can understand any of this at all is remarkable. Consider what we've discussed: dead stars, gamma rays, neutron matter, magnetic field decay, fast radio bursts, starquakes. None of these concepts are obvious. None reveal themselves naturally during ordinary life. We learned about them because generations of scientists observed carefully, asked questions, built instruments, tested ideas, and shared discoveries. The story of magnetars is not only a story about stars, it's also a story about curiosity. The first mysterious burst could easily have remained unexplained. The signals were brief, the objects were distant, the observations were difficult, yet researchers persisted, year after year, decade after decade. Eventually a coherent picture emerged. Not a perfect picture. Science is never finished. But a picture detailed enough to transform mystery into understanding. There is something comforting about that process. The universe may be vast, it may be strange, it may occasionally seem indifferent to human concerns, yet it remains understandable. Perhaps not completely, perhaps never completely, but enough to allow progress, enough to reveal patterns, enough to uncover stories hidden within the stars. And what a story this particular one turned out to be. We began with a simple question. What is a soft gamma repeater? The answer led us through stellar death, neutron stars, magnetars, giant flares, starquakes, hidden oscillations, and some of the strongest magnetic fields known to exist. Along the way, we discovered that dead stars can remain astonishingly active. We discovered that magnetism can rival the power of stellar fusion. We discovered that explosions occurring across the galaxy can leave measurable traces here on Earth. Most importantly, we discovered that endings in astronomy are often less final than they appear. A supernova marks the end of one story. A magnetar marks the beginning of another. That pattern appears throughout the cosmos. Matter is recycled. Stars are reborn. Galaxies evolve. Change never truly stops. The universe seems remarkably reluctant to remain still. And perhaps that's why soft gamma repeaters are such fitting subjects for reflection. They are reminders that activity can persist long after we expect it to vanish. That transformation can create new possibilities. That even objects we casually label as dead may continue surprising us for thousands of years. Somewhere out there tonight, beyond the clouds above your home, beyond the planets of our solar system, beyond the bright stars visible to the naked eye, ancient magnetars continue their slow evolution. Most are quiet, a few are restless. One may release a burst tomorrow, another may remain silent for centuries. The galaxy carries on, the stars carry on, the remnants carry on. And while those distant objects continue their long journeys through time, perhaps your own evening is becoming quieter as well. Maybe the room around you has grown still. Maybe the day feels a little farther away than it did an hour ago. Perhaps the details of magnetars, neutron stars, and gamma rays are already beginning to drift gently into the background. That's perfectly all right. After all, the goal was never to memorize every detail. The goal was simply to spend some time exploring one of the strangest corners of the universe together, to follow a mystery, to satisfy a little curiosity, to appreciate how wonderfully surprising reality can be. And if, somewhere between a giant flare and a distant magnetar, sleep has begun drawing closer, then our journey has served its purpose. Thank you for joining me here on Science for Sleep. Until next time, rest well, stay curious, and remember that even in a universe filled with endings, some stories continue far longer than anyone expects.